Hi, everybody.
Yeah, so
I'm not a professor. I work at Unifor, and I'm working on speech and natural language AI for corporate applications, business applications mostly. Um, and I will be giving a summary and a survey of speech and language modeling, language modeling techniques applied to speech, I should say.
right. So you if you been in ENLP for in I think it's 2014, right? Andreas gave a keynote there, right? Or
Oh, you are so behind the times. I've been doing this for since the 1990s.
yeah, so well, so I think for today it's quite special. Larry and Andreas is my mentor both academic wise and career wise. So I'm quite
Yeah,
fortunate to have them, and each of them gonna sharing different perspective. And as Andreas say, oh, all right. Sorry, there's a connection issue.
I can hear you. No problem.
All right, the clicker. All right. So from the Andreas side, like although he had both a lot of work in the NLP and speech, but he will come over about how we migrate from the ASR language model to ASR large language model. And we also have Andreas, former collaborator Hua in person from NYU Shanghai and NYU. She will sharing something from AI to HCI, speech plus HCI, especially on the value alignment. All right. Yeah, finally myself. Yeah, so I'm from NVIDIA. So my background is like speech recognition, but as far more recently in the past 3 years, I'm working on speech language alignment. And for today, I wouldn't share something I shared before in the interspeech tutorial. So I will more sharing about something from the agent side. So we're going to talk about speech agent and reasoning. So we really look at something the next, what kind of new problem we're going to tackling and leaving some open direction there. And it's like it'll be boring if we only have our own things. So I'm fortunate to invite Xiaomi's ALN core team's principal researcher who released the Mimo audio quite recently, open source, open commercial using. He will also give a spotlight tour for 15 minutes to share about their recent work on Mimo audio on the full duplex model. All right, so I think that will be the structure today. It was like both fundamental and something advanced. And here's a even more high-level overview. We can see in this tutorial, you're gonna learn from agent, speech and language model, and multimodal conversation reasoning. And we know there's many ways to define artificial general intelligence, but for this session, we're gonna look at something between speech and text. And we want to have a shaking hand between acoustic model and language model. And we have Larry, Andreas, myself, and three like sensational spotlight speaker. And then I'm really happy to have Larry for our first session. Please, Larry. Thanks.
Okay, great. I'm going to share my slides here.
Oh, by the way, after each session, we have 5 minute Q&A, so you don't have to wait at the end. So yeah, and we don't have a break, so feel free to take a break during the QA section. Yep, Larry, feel free to take over the screen.
Yeah, I think you have to stop sharing so that I can share.
All right. Hello. Can you stop sharing? Oh, sorry. Yeah, can you do stop sharing? Appreciate it.
Okay, there, that's good. Okay, how can you see my screen?
Yep.
Okay, so I'm gonna
Uh,
talk. Yes.
all right. So maybe we're gonna do the outline a little bit. Can we have the full screen or it'll be like this? All right. Yeah, sounds good.
Okay.
Please go ahead, Larry. Sorry.
Okay. Uh, so I'm going to talk for the next 40 minutes, and at the end of my talk, like Huck said, we have an invited speaker, which is Gokin. Let me go ahead and get started. I'm going to talk about conversational systems and agents, and I'm going to talk about the last 10 or 15 years and the evolution of the technology as it's gone from, the early systems that we think about, like Siri. So 2011, Siri came out. After that, Cortana and Google Assistant and the others. So there's been a lot of years of development on these core virtual assistants and at different companies. And what we're seeing is this transformation from the core technology stack as well as the user interfaces from those old personal assistants to what we're seeing now, for example, ChatGPT Atlas. And back in 2012, so 13 years ago, I gave a keynote at the SLT workshop, and the keynote was titled The Conversational Web. And what I was describing, and I'll talk more about it in this talk, was sort of a future vision of how we could, modify and extend the virtual assistants to someday have capabilities so that using the web should be as simple as having a conversation. And in what, 2 weeks ago now, ChatGPT Atlas was released. And ChatGPT Atlas integrates chat, search, browsing, and agentic functions, the web as a single conversation. And so this is a realization of this conversational web that I'm talking about. So there's a lot happening right now, a lot of excitement of this new technology. So I'll talk about that. But stepping back, where were we 15 years ago? The state of the art at the time was, monolithic single agents. The task that we were working at the time was primarily AI skill routing. So we were trying to determine the domain, the intent, and then slot specific information. Let's say someone's trying to find a flight. The slots would be things like, the time of the flight and the number of people. And so the purpose of that, the main focus was if we could extract the slots and we knew what the intent was, then we could call a backend API, let's say like Delta Airlines, and then satisfy the user's need. The systems were composed of modules, so separate modules like speech recognition, and then we had a semantic decoder and state tracker, separate dialogue policy. The generation was separate, and then we had separate TTS. So everything was very modular, and the systems were completely separate from the web. So these were standalone walled garden. So there was no direct leveraging of web search and browsing. And at that time, some of us that were working on, the early days of Cortana at Microsoft, we're kind of questioning that. Why are we not leveraging, web search and browsing? And so I'll talk about some of the early work that we did in that direction. So today's assistants, a lot of the components that you see on the left have been taken over by large language model, and they're multi-agent. You have unified AI skill modeling, where the LLM takes on the responsibility of, determining what the skill is that you want the assistant to have, and then call the function or the API or the tool that will satisfy the need. So the LLM is taking on a much broader responsibility, covering many of the subcomponents we had before. And what I think is super exciting, especially like I said, just recently with the release of products like ChatGPT Atlas, these are native web search and browse assistants. So they have awareness and can actually take action on the web. And then what we're going to talk about in this tutorial is extending that even a bit further, which is complete end-to-end multimodal I/O. So speech, text, vision, and we'll go into great depth. I'm going to give kind of a high-level overview of the conversational systems and agents, and then Andreas and Huck will get down further into the details of the back-end models. But I think it's safe to say that what I was talking about 13 years ago, the conversational web, that is actually being realized now today. So just to say a bit more about what the conversational web is going to give us, right? So this idea that we're not talking about complete automated systems. We're talking about kind of like a browser would, and search capabilities would, which is to augment humans. So humans plus AI. And so that these AI virtual assistants or AVAs can give you kind of extend your capabilities. And of course, we've had search for a long time, and we've had browsers for a long time, but connecting that to natural language so the interface with humans is much more seamless, is super powerful, gives us superpowers. So there was a book that Bill Gates put out in the late 90s, I think it was 99. It's called Business at the Speed of Thought. And I really like the concept of that book. He was talking about the role of technology is to take some thought that you had for the business and just execute it for you, right? So that if the technology is, doing its job, it should automate that. But the original thought is coming from the human. So kind of staying with that theme, the conversational web is in our different areas that we work in is kind of extending us. And so let's say you're a researcher, and so a virtual assistant with the conversational web, you have access to all the information, and Google Scholar and other sources would be like a research assistant at the speed of thought. Or if you do what I do, in addition to research, I teach, so a teaching assistant at the speed of thought. Or let's say a legal assistant at the speed of thought, where you don't, in this case, to have to be an AI expert, but you're going to be using the AI to extend you. Or a medical research, a doctor's assistant at the speed of thought. And then even in the creative arts, composer's assistant, artist assistant, writer's assistant. So this notion of extending humans is super powerful, particularly with the connection to the web. So in that keynote, there were two major research themes that actually had four, but these are the first two that I was laying out in terms of the future directions of things that we really needed to work on. And the first one was adapting to context. So these virtual assistants could be grounded visually or on a web page, could also be grounded by information about the individual, the personal information, or in the dialogue history. The second theme is leveraging what I call the taxonomy of the conversational web. So I'm going to start with the first theme, which is adapting to context, which is actually a lot of work that's going on right now in this area. And I'll talk about some of the work that I've been involved with, sort of from my perspective, in grounding. So here's an example of different type of content that you might ground a conversational system to. It could be forms, it could be tables, figures, it could be textbooks, maps, technical papers, all kinds of things that if you have a conversation over or on top of this information, you could ground the conversation to that information. And there were a couple papers that I was involved with that kind of go into more depth. The first one was in 2022. It's a multimodal conversational AI survey. The other one was with Stanford, some people at Stanford that I was working with, which is grounding open domain instructions to automate web support tasks. And by the way, all of the papers that I cite on the slides, I put them at the end of the references so that you can find them later. So with this kind of concept in mind of grounding to this web content, let's step back in time. This is a really early demo. This is something we put together at Microsoft. This is in 2013. And what this was this idea that we could have conversations in our living room as you're talking to the TV with a browser. And so in this case, the human is actually powering the browser experience by voice and gestures. So if you see down in the bottom right, it says feedback windows, and there's a little skeleton. That was use of Connect to actually measure gestures and that sort of thing. So let me play just a little bit of this. Hopefully you can hear it, just so you can kind of get an idea of what the world was like back in 2013 in grounding on the web.
I'm in the mood for Italian food.
Okay, I'll look for Italian restaurants in Redmond.
Show me the family-friendly ones. Between $20 and $30 a person.
So now she's going to gesture. You'll see it in the
Scroll
bottom,
down.
in the bottom right. And you'll see the mouse.
Show me the menu for this one.
Okay, so at that time, what was powerful about this was that this system adapted each page on this fly. And so at that time, speech recognition was not nearly as accurate as it is today. But if we adapted the language model by scraping each web page as we went to it, actually we could perform very accurate speech recognition. And then that enabled us to then do accurate intent classification. And this, the system actually worked quite well. The gesture part of it was interesting. If you see the plot here, this is missed probability and false alarm probability. And so bottom left is where you want to be. The lower the better in terms of errors. And the black and the red line versus the purple and the blue is when you actually use gestures in combination with speech. And so that was very eye-opening to us that we could dramatically improve the accuracy if we allowed gestures. So that led us into this next work, which was eye gaze tracking. So again, this is with a conversational search and browse, but now we have an eye gaze tracker. And what we found in this was if you could track what someone is looking at while they're speaking, you almost didn't need speech recognition because it was pretty clear what the person was trying to do. And you can see the numbers here. We were comparing just using speech alone or gaze features alone, and then combining the two is a really significant improvement. So that was also an early stage. And what's interesting is some of these things have not really gone out as products yet. They're certainly possible to do that now. Third area in conversational search and browse is form filling, because you might imagine you go across the web, you're going to see a lot of forms that you have to fill out. And we did some work back in 2020 and then extended it in 2024. We called it M-Forms, multimodal form filling with question answering. And so the basic idea was if we could semantically understand the visual layout on a screen, in this case it's a mobile screen, and then identify different elements on the screen and what they might mean. So we're using computer vision to do that. And it's a vehicle logger, and the computer vision system is identifying that there's radio buttons, and then there's some information like odometer value, that sort of thing. So the trick that we came up with that we found was really useful was we could actually have the system, the computer vision system, once it identified what the elements did, could synthetically generate a question that someone might have asked actually related to each of those elements on the screen. Now that's synthetic, and it's actually something that's only used behind the scenes, because really what we have with the user is just, if you look up here in this visual slot NLU, is just the utterance. So the person says something because they want to, let's say, log a trip, and they say something. All of the visual elements are asking questions, sort of behind the scenes, like, hey, would you like to log this trip as business, personal, or other? There'll also be a question like, would you like to enter the odometer value? And so then we have questions, and then the person has the utterance where they say, I actually want to, select business. We can set this up as a question answering system. So the questions are actually generated synthetically by the computer vision system. And of course, the utterance is from the user. And if you do that, then you have a question answering trained system that turns out it's zero shot. So you don't have to actually do any training for any form, as long as you have the computer vision system. So what this shows is the power of the computer vision to set this up, or to transform this problem into question answering. And the result we got was on ATIS, air travel information systems, that we got state-of-the-art F1 results on that with only 1/10 of the training data, because we were leveraging this grounding with vision. Much more recently, we put out a data set called Hidden Forms. The data set is to facilitate and advance research on systems that have to understand forms and fill them by, visually predicting what parts of the form perform what kind of functions. So this is a data set of NL commands paired with these masked or obscured visual elements on the UI. And so if you look at the examples here, you have in the upper left the original UI, and then there's different variations of masking that we're posing in this data set, and a challenge for the NL system, or the conversational web system. The first one is just static, where it has to figure out like, for example, the flights, the form element. We show a high contrast and low contrast in the C and D. Low contrast is probably more realistic about what kinds of tasks you would see. So the system has to figure out, what should go where. So this data set was released, and you can see the statistics on the data set here. This was this year. So form filling is still really important, and still active area of research, definitely. Okay, so another really important element on the web is tabular data. So here's an example where we have some table, let's say it's like a Wikipedia table of Canadian state funerals. There was original data set that was a single shot that was converted into a multi-turn conversations to support conversational interactions with tables. And so the blue question and answer is what was created for this data set. So this example says, the question is, hi there, do you know much about state funerals in Canada? And let's say the system says, yes, indeed. These are public events, and so on. And the person says, okay, I see. Do you have a list of state funerals? So there's a kind of a sequence back and forth, a conversation back and forth to get information from a table, or a table that is pointed to by this table. And this data set was created back in 2022. It's called Hybrid Dialogue. So we used this data set, and we developed some algorithms actually to support conversational interactions with tables. And you can find details about this in our 2023 paper. But basically what we did is we had 3 stages that we set up. The first is a dense table retrieval. Basically, we created embeddings at the table level, and then the state tracker, we created embeddings at the cell level within the table, so that we had a cell encoder. And then we fed all of that into a large language model. We had a question encoder so that we did the matching, and then we used that for question answering. And when we did that, we did some human evaluations. We significantly improved, 84%, 82% improvement over the state of the art at the time in coherency and fluency for our system. And then if you look at informativeness, which is basically where the model response is semantically equivalent to the ground truth, we went from the state of the art from 12% up to 50%. So this was a significant advance forward. Still a lot more work to be done on tables and conversations with tables. Okay, so going back to adapting the context at this high level, there's other types of content that could be leveraged. And I've talked about, conversational tables and forms, that sort of, but if you up level and think about scientific papers, and where the scientific paper forms the source of grounding for your conversational system, then you can start thinking about question answering over scientific papers. Let's say for us, that as you're reading a paper. We released a data set at NeurIPS, which is called C papers, or conversational papers. And this data set was created so that it would support conversations, not just at the high level like you might try right now with ChatGPT on a paper, but at a lower level where you could actually ask questions specifically inside the paper, like questions about figures, equations, tables, that sort of thing. So here's an example of a conversational figure. And what we did is we wanted these questions to be representative of the kind of questions that researchers would ask. So we went to Open Review, and we went to the archives, and we scraped information. So we got the original paper when it was in archives, and then we got the paper that was published at NeurIPS and other conferences. And then we got the Open Review on that paper, and we got the questions from reviewers and the responses back from the authors. And so, for example, in this case, let me move this down here. This is a question about a figure that you see in the bottom center. And the question in this data set, or this benchmark, is, in figure 9, could the authors clarify what the cross at the center of the image indicates? And the answer, which is now this is going to be the task for your conversational system, has to be able to come up with this answer, which is, in figure 9, the cross at the center of the image represents the input values of the parameters used in the simulation. So the questions are more detailed, more sophisticated, more appropriate for the kind of questions that you might have if you're a researcher reading this paper. This is on figures. Same thing on equations. In equation 2, the paper introduced the temperature parameter tau to control, and so on. So you can see that this data set is going to be pretty difficult, but I think also pretty appropriate for the kinds of tasks, questions that we might have as researchers over papers. Okay, so now beyond the conversational content, we can actually think about other sources of grounding for conversational systems. And this could be in the web, but it also could even leave the web. Conversational vision is, of course, an example of this. Conversational knowledge, in this case, personal knowledge to common sense, to inference and reasoning kinds of knowledge, which it provides, if you think about it, a grounding or a context for the conversation. And another area which you don't hear as much about, but we're doing research on this, which is called, and I'll talk about it in a second, which is called conversational expression. Especially what we're working on is emotions in large language models. So I'm not going to have time to go through the conversational vision work. I show some of the work I've done, and then I put those also in the references in the back so you can look at that. But I will start with conversational knowledge. So the question about large language models that's been asked over the last 2-3 years is, do large language models actually have common sense? And of course, common sense is needed for next generation conversational AI systems. And so as this question has been posed, initially the answer was no, now the answer is sort of, but I think people that have worked on this can agree that, common sense is actually a pretty difficult problem to work on. So one of the things that we did was called Syndicom. We were improving conversational common sense by injecting errors and then using NL feedback. And so this was back in 2023. just to give a high-level summary of what we were doing, what we found when we used crowd workers was they're not good at a lot of things, but one thing they are good at is if you show them a conversation and where there's an error that you've injected into that conversation in terms of common sense, they can easily detect this and actually very efficiently detect this. So when we realized that, then we started putting data sets together where we would just throw a wrench in the middle of the common sense logic, and then not only have the crowd workers spot it, but then give an NL feedback, an NL description of why it didn't make sense. And then instead of just using the label that it was correct or incorrect common sense, we would actually also use the NL description and inject that into the improvement. And that actually, the NL feedback gave a significant win over what you could do if you just had a labeled conversation with it being correct or not correct. So that feedback, this is like an example that, crowd worker 1 and the explanation says, this contradicts what was said about impressing people, with this conversation. So there's more detail, more information that you can actually inject into the training of the system. And with this method, we actually improved the state of the art quite a bit. Let me pull this down a bit so I can see. Yeah, we doubled the improvement over ChatGPT 3.5 at the time. Okay, another area of conversational knowledge, which is getting some attention now, starting to grow, is this idea of model editing. So model editing is either injecting knowledge or forgetting knowledge, but without retraining. Retraining these large language models is extremely expensive, approaching $100 million. So without retraining, can you actually go in and tweak the numbers on each of the weights of the large language model and then inject whatever knowledge you want, or forget it, remove or machine unlearn knowledge? And unlearning is really important and has been important for quite a while, which is this idea of the right to be forgotten. Also, the GDPR regulations in the EU, where individuals want their personal information or even just information about them that's not necessarily personal, but something they don't want in the large language models to be removed. So this is becoming an expensive thing to adhere to unless you have this kind of technology. So in my lab, we created what we call unlearn or learn, this algorithm that injects, forgets knowledge without impacting related knowledge. That's important. So we don't just forget knowledge, but we sort of surgically forget it in a way that doesn't damage the knowledge that you want to retain. We edit the large language model weight simultaneously, very efficiently. It's a subspace method. It's a geometric linear algebra kind of approach. And like I said, it discriminates from the knowledge you want to remove from the knowledge you want to keep. And then we published this at NACL. So here's an example of some results from Unlearn. So what you're seeing here is a bunch of different data sets. And what we've done is we've trained the system, fine-tuned the system on the training sets for these data sets, and then we tested them. And then we've normalized the scores so that what you want to see is 100% accuracy on this data set means that you've remembered everything about that data set. But in this particular case, we used our unlearn algorithm to target one of the data sets, in this case, natural questions. And we said, okay, although the large language model has been fine-tuned on it, what we want to do now is, without having access to that data, we want to actually come in and edit the weights and try to remove that knowledge from the large language model. And you can see we drop the percent of knowledge retained quite a bit successfully on NQ. Just to compare this with other methods, state-of-the-art methods, here's the state-of-the-art method before ours and what it was doing. And you can see it does a pretty good job of this gradient ascent method of removing knowledge about NQ, but unfortunately it also removes a bunch of knowledge from NQA, which is narrative QA. So here's our method and then their method. So another area of conversational knowledge is personalization, personalized continuous learning with small language models. So complex large language models are difficult to train with a small amount of data, like in tasks like personalization, and they can't run on device. So people typically have been exploring small language models. They are computationally cheaper, these SLMs, but they lose the breadth and quality of the conversational interactions. So we came up with a method we call it LEGO, which stands for Language Model Building Blocks. And the idea is that we start with a large language model and we break it down into parts, but we break it down carefully so that when we break it into these pieces, we know that we can reassemble them back to the LLM. Each one of these pieces you can think of as a small language model. It could be for an individual. So we break out a portion of the large language model that's most relevant for an individual or a task or some subset of knowledge. And like I said, the sum of the parts, we can reassemble this from all of these parts back to the LLM. It's very efficient because when we implement the system, the SLMs, we use a federated learning architecture. And then we can personalize because each of these Lego blocks can be optimized for person, task, or device. Okay, so going back up to the sources of adapting, of grounding so that we can adapt to context. We're going to talk about conversational expression just a little bit. So conversational expression is something that has not received as much of attention. What I'm talking about here is what I would call the affective conversational web. That the emotional context of a conversation can convey a lot of information, but it can also inject a lot of noise. If you had an emotional or angry response, or let's say there was sarcasm that was in the conversation. Today's conversational assistants still struggle with understanding, the emotional context. So how do we, on the other hand, there could be some useful information, and particularly as we're starting to use more and more social media to train large language models that have a lot of emotional context. So how do we disentangle this emotional expression from the content and sort of neutralize its confounding effects so that we can get at the knowledge? So we very recently, this year, we've been developing a method we call latent space guidance. And it essentially does this disentanglement of content and emotion, but it also allows us to sort of steer the emotional content. So we could take some emotionally charged statement and we can neutralize it, or we can change it to another emotional state. And then it's very efficient, the methods that we're using. And we're getting, significant gains on question answering accuracy by identifying these emotional questions, or in this case, actually, it's the context for the question, and then neutralizing it. And you can see here. Okay, so I've talked about adapting to the context. I'm going to switch gears on the second part just to talk a little bit about the taxonomy of the conversational web. What do I mean by taxonomy? Well, on the web, in early search days, there was this taxonomy of the web. Taxonomy of the conversational web is an extension of that, where you have navigation, information, and transaction as intent for, in this case, conversational search queries. But as I've been talking about, you also have this context, this conversational context. And if you think about this, you can think about this kind of on a two-dimensional grid where you have conversational intent and context. And then you look at the different intent, and you could talk about, let's say, transactional entity, where you have a single entity, which is a context, let's say on a web page, and you want to make a transaction, like perform an action, like book a table for two. So that's kind of the idea of how to break this down. And you could think about this at the level of collections or pages all the way out to, vision, and think about how each of these intents map over to that. And if you look at this and the conversational web and think about transactional this is the doing of the web, or AI of doing, as opposed to AI of knowing. And this is where agents comes in. So what is an agent? So an AI agent is a software system that can perceive the environment and reason over it and make decisions and take actions. So you can see on the right side here, with the LLM and extending capabilities of the LLM, or inside the LLM, you have reasoning capabilities, planning, and you can take actions. And there's tools that you can use for doing this to interact with the outside world. So tools are part of an LLM agent. The agent itself examines or observes the environment, has to make a decision on what action it should take based on what it's observing. And there's some language instruction. So you might have something like, book a flight from San Francisco to New York. This is given the context of, let's say, a web page. And you know that the actions that you can take on that web page are things like clicking and selecting from drop downs and that sort of thing. So this is very much like I showed you that, or played that little clip for you in 2013 conversational browser. It's just that now we're going to be using AI agents to actually pose these questions or these statements. So there's been a lot of work just in the last couple years, 2 or 3 years, on conversational agents, particularly around reasoning. One area or one method for reasoning that has become very popular is called React. I'm not going to talk much about this because we're going to have a special session right after this that Gökhan Türe is going to talk in detail about React. But basically the idea is that you in the prompt get the system to observe and then come up with a thought and then take an action. So it's kind of like chain of thought reasoning applied to agents. When you think about benchmarks for agents, Web Arena is a really important one. So Web Arena is a sandboxed approximation of real websites, but it has a lot of the complexity of live interactions on the website. And it's become very popular. It's actually now inside of sort of a broadened set or environment, I should say, for doing these evaluations. So Web Arena now is which is called Browser Gym. So Web Arena is inside there along with a MiniWob and other kinds of benchmarks. If you want to get in this area and start doing work on conversational agents with tools on interacting with the web and web browsers, I definitely recommend looking at Browser Gym and looking at their leaderboard, and they have code set up so that you can get going really quickly. That's a great place to start. So why do agents need APIs and tools? Well, of course, to do something, you have to enable real actions besides just having a conversation. But it also provides access to knowledge that may be dynamic or externally modified. And you're accessing information, extending capabilities beyond the LLMs. But then why is it so difficult to call a tool? Well, there's a lot of details that actually go into. First, you have to detect that you need to use a tool that the LLM cannot actually solve the problem internally. You have to go external. So you have to detect that. Then you have to figure out what is the proper call to the tool, if it's an API or SQ or SQL. And then you have to parse the output, the response back, and then feed it back into the LLM and then make the final answer. And all while staying in the conversation. You don't want to have this conversation depart. So there's been methods have been developed, a lot of methods actually for tools, but I'm just going to talk about 3. First one is Toolformer. Toolformer teaches the models to call the APIs, and it trains the models for that. So basically the model inserts candidate API calls into the text, and then it does this by a next token prediction. But in this case, it's next token prediction with an API call. And so this kind of kicked off a lot of work that people have been doing in using tools and agents, external tools and agents. That's a really important paper. Gorilla is another paper that came out. This paper was specifically trying to train systems to understand LLMs to understand how to call APIs by using sort of a combination of the LLM and a RAG-based system, so that you had this API database, you do information retrieval, and you basically classify or retrieve the information of the API call, and then you fill in the API. And so this is also a really important data set. And then Tool RL, this was actually done by our next speaker, Gokun and company at UIUC. This paper was called "Reward is All Tool Learning Needs," and what they noted was that supervised fine tuning of LLMs for tool use, like what you saw in the previous slides, struggles to generalize, particularly in multi-step reasoning. And so what they explored was reinforcement learning. And that there's a lot of promise there, but designing the reward signals for tool use was non-trivial. And so the key contributions of their work was a systematic study of reward design, because that was the hard part, and then a principled reward framework, sort of decomposing the format and correct tool invocation. And then they used a GRPO method that gave them 17% improvement over base models and 15% over the supervised fine tuning. So these are some of the benchmarks that you can look at if you're going to be doing work in conversational agents with tools. Okay, so just a closing thought here. Back in the 2010s, with the advent of Siri and Cortana and others, systems were very modular, and we were pretty limited in what we could do back then. But what I was thinking about in 2012 and hoping for, and laying out kind of a vision for, was a conversational web where using the web. And I think what's happening is that is the conversational web today. It's just using the web will very shortly be as simple as having a conversation with a combination of all the work that's going on, not just what we're doing, but all the work that's going on and adapt into context, as well as the development of conversational web agents. So I put references at the back, but thank you very much.
Yeah, thanks, Larry, again. Right, so I think we can have 2 questions, and if you have more questions, feel free to leave the question in the underline. Yeah. Anyone, if you have a question, please go to the microphone. Larry, I have a question for you.
Yes.
Yeah, so in your perspective, what could be the real challenge if we apply a conversation agent to the real world, or as a something like ChatGPT moment for conversation agent with the web or with the real world?
Yeah, one of the things that so I've been spending a lot of time this year actually trying to implement some systems, and one of the things that I realized was a real challenge is to decide where you cross over from the point of sort of the AI of knowing to the AI of doing. And by the AI of doing, what I'm talking about, for example, is where you want the agent to actually go out and control your browser and click on buttons and fill forms, do things for you, which is very powerful, but it's also very slow. And it's not necessarily appropriate for all things, many things. And so, using web search as a tool, as a function inside of, for example, OpenAI Agent SDK is super powerful. It sounds like it's an old idea, but it's tightly coupled and tightly integrated so that, let's say you're trying to book a venue, and you're planning a party or something, and you're trying to book a venue. You can find out the opening times, the closing times, availability, and all these things without actually doing anything beyond web search by using these kind of integrated tools. So the big challenge, I think, is, where is that crossover line where okay, now we need to actually have agents that go do things on the web, or should we actually be, staying on the AI of knowing? I think that's a big area.
All right. Any other question? Yeah, I think that is a great answer. Oh, please go ahead. Is Gokhan here already?
Yeah, I am here.
Oh, hi. Yeah.
Hey, Larry. Great talk, so thank you. How do you think the web will change to accommodate, I guess, these conversational agents?
Yeah, that's a great question. One of the things we thought would happen 15 years ago with the semantic web coming on the scene was that, everybody would label their websites with, schema.org, and, things would be so much more powerful. And, what we found is that people don't necessarily do what you want them to do to solve technical problems for you. So it's a similar kind of thing right now is, well, it would be great if, instead of having to have these agents go out and interact with browsers, if the APIs, would adhere to basically MCP, which has become, standard, so that developers would say, okay, let's just register, access to our backends through MCP, and everybody does that. Then you don't have that, you can basically bypass having to interact with a browser, and it becomes much, much more powerful. So this time, I think it might actually happen. I think people are understanding the urgency for taking their businesses or making their businesses sort of AI enabled, and understand. And I think people are broadly starting to understand that, okay, we need to do some work. Let's actually integrate the way that we can, so that we're relevant. And I think MCP is going to really, it is already starting to take off. So I think that's a big change of the web, is going to be this kind of MCPing of the world.
Awesome. Thank you.
All right. So if I have more question, I think you can leave your comment on the Zoom link in the underline, and the author may reply. Yeah. From Larry. So yeah, we are really happy to have our special invite talk from Gokhan, Professor Gokhan Tool from UIUC. I think for people in the field may know Gokhan and Dilek for a long while. And Larry, did you have some word for Gokhan? And then we will let Gokhan to start.
Yes, that would be great. So Gokhan and I have known each other for a long, long time. Gokhan started at, well, I think we intersected at SRI. That's also where Andreas was. But then when I went to Microsoft, I had the pleasure of working with Gokhan and his wife Dilek, as well as Andreas and Liz. And we formed this team, which became sort of the founding team for Cortana. And so we spent a lot of time working together there. And then Gokhan and I joined up again at Google in Google Research. And then from after we worked there, Gokhan went to work at Amazon for a number of years. And he was at Uber for some time. And then ultimately now he's a professor at UIUC. And I think that that's a fantastic transition from industry, because that's what I did. And I think he's enjoying it. I'm certainly am. So very pleased to that Gokhan agreed to give a guest talk on this.
Thanks, Larry. So should I share my screen, or you will control it?
You can share a screen with the audio, please.
Oh, okay. So can you see my screen?
Yeah.
Cool. Yep, thanks, Larry, for the introduction. Sorry, I missed the first part of Larry's talk, so there can be, some overlap with our contents because we have, very similar, background. So yeah, as Larry said, Dilek and I are co-leading at the Conversational AI Lab at UIUC. So this is a newly formed lab focusing on conversational agents. And this is like a very, very brief, history of task-oriented dialogue systems. Nowadays, people prefer to say conversational agents. Despite, most people think that conversational agents started with ChatGPT. Obviously, they didn't. Actually, it started in the, speech community, late 80s, early 90s, with speech recognition system. First, small vocabulary speech recognition system, then larger vocabulary speech recognition system. At that time, Nuance was a spin-off from SRI. Larry was involved with such systems. And then the goal was basically helping with call centers, trying to understand the intent of the users, and then take actions accordingly. And then there are two big earthquakes in conversational agents. The first one is thanks to Siri. Siri is another spin-off from SRI. And then, as there is said, Andreas, me and Larry were part of SRI, and Andreas and I actually work on this DARPA Kalo project, which is the precursor of the Siri startup, and then Apple acquired it. And then when Apple acquired Siri, we moved to Microsoft, funding Cortana, and then many, many other systems followed. And then the second, big earthquake, of course, came with ChatGPT. And then this was so big, it also came with a tsunami. So it has resulted in a huge explosion in the field. And then it changed many of the things, we have been doing. So this is like the textbook architecture of a task-oriented dialogue system until ChatGPT. We were always saying that a typical dialogue system has 4 components: language understanding, state tracking, dialogue manager to keep track of the policy, and response generation. And then if somebody says, book me a table at Pascal for 2 people, the goal of language understanding is convert it into a structured form like an API. You can think of it as like function calling. And then, you interact with the backend API or database, and then dialogue manager tells the response generation what needs to be done. So dialogue manager decides on the action. And the response generation converts it into natural language. Of course, with LLMs, language understanding and dialogue state tracking is now happening in a single LLM call. And then dialogue manager and response generation is happening another LLM call. You cannot do the whole thing with a single LLM call because in the middle you need to just run the API, right? So you need to get the API response to decide on what to say to the user. So this is another way of showing the same thing. So user says, find me a restaurant in Los Altos. You do one LLM call, and then you get your function call. And then you run that function call, and then you get the output, like there are 18 matches, and then go to the LLM, and then LLM decides on what needs to be done. Like, do you have a preferred cuisine? And then user can say, I like Italian food. So every turn is like 2 LLM calls based on whether you need the backend call or not. So as Larry mentioned, a very well-known framework to achieve this is proposed by Google folks in 22. It is called React. React means reason and act. So reason basically means thinking, and then act means the response. And then again, for each turn, the system just thinks what needs to be done, acts, thinks, acts, thinks, acts. So it can be a series of these things. And then if there are some outside external API calls, they can also be handled accordingly. So this is basically designed without thinking of conversation. So when people proposed agents after seeing ChatGPT, they simply thought that, okay, user will ask something complex like, do a, deep research in this topic, prepare a summary, like a 2-page summary of this topic. Or even, some hypothetical tasks like, okay, go bring me like $1 million, and these are the stock operations, you can use, and here is hypothetical $10,000. So it is designed as if the agent will go and then just work on the task, and then it will have many, many steps while achieving this task. And then it will come back with the result. So this example on the screen is showing a robot task. So you give all the information to the robot, all the context, and then you tell the robot, okay, now put some pepper shaker on a drawer, right? And then no conversation is needed. So at the end of this thinking and acting, you check whether, robot has put the shaker in a drawer.
Gökhan, are you still there? Andres, can you hear Gökhan or?
No, I can't. I cannot hear Gökhan.
All right, Gökhan, we are missing your voice.
Oh, okay.
Right,
1,
right
2,
now it's
3.
good.
Yeah,
Okay.
that works. Yeah.
Okay. Yeah, even yesterday's Kimi K2 model, they are proud that it can handle 300 consecutive function calls, right? So the whole thing is designed as if this thing is handled by a sequence of actions without even talking to the users. And this is one example for AutoTaught, for example. So we say, oh, okay, we are an intelligent assistant for restaurant reservations, and then these are the functionalities, and then you need to think and then act. And then this is, very simple prompting. And then the problem of this type of language agents is that, it is missing conversation. And I think, this is the #1 topic of this tutorial. So anybody can write a prompt to an LLM, and then LLM can take actions, right? But what about the interaction piece? So in traditional dialogue systems, this was basically handled by the dialogue manager. Now we are missing the dialogue manager. So previously, the dialogue manager was the brain of the dialogue system, deciding on what to do at that stage in a dialogue, steering the dialogue. Now, with the current agents, we lost that capability. And then just think of simple policies. And these policies can be, very simple business rules, like you are building a financial agent for a bank. And then, user says, transfer $10,000 from my savings to checking, right? Any financial institution have lots of rules, like if it is above some certain limit, do this, confirm with this, with the user, and then check, this, check that, lots of controls. Same thing with like cancel my annual subscription plan, when you are, I don't know, talking to a Netflix agent or something. So these policies are usually if-then-else rules, but they are so complex. There are, thousands and in some cases millions of them. Just think of a simple restaurant search example I provided. Like if the backend, said there are 18 restaurants, are you going to list all 18? Or are you going to just, maybe mention the best one and then say there are 17 more? Or, you will ask a, follow-up question to filter the restaurants further. Currently, if you don't say any policy rules in the prompt, it is up to the language model. And then we call this prompt and pray. You are just relying on the model's feelings at that point. Model may decide to ask, or it may not. For example, just before this talk, I said, I asked ChatGPT, give me a soup recipe, and it didn't ask me a question, and it gave me a random, soup recipe. Similarly, for the robot, I tell the robot, make me a salad. Do you want the robot to make you a random salad? Or, do you want the robot to be more interactive and then just like a human, chef, maybe asking you questions and then discussing the options with you, like what about tomatoes, what about lettuce, etc. And, this is much more natural, right? But this implies interaction. This implies conversation. So there is a need to move from language agents to conversational agents. So this is, why we published this paper, Respect. Instead of, reason and act, now we are reasoning, speaking, and acting. Speaking implies conversation here, and then mostly proactive conversation, like system is asking back to the user. So this is some capability current LLMs are lacking greatly. And then this speaking functionality will be basically acting like a dialogue manager. And then whenever there is an ambiguity, there is something not clear, you need to ask some clarification question. Agent is supposed to just, ask the user. And it is also the same case, when there are two agents interacting or collaborating towards a common goal. And then how you can do this is there are two ways. Either you augment the prompt with such policy rules. And then there are, a couple good papers like Flowbench exploring that. And then currently we are in the works of publishing a follow-up to Respect. We call it Speak RL. So it is basically an RL-based approach to decide when to get back to the user, because you don't want to ask user every atomic step, right? And then you don't want to just try your best for the test, so you need to find a balance. So what are the optimum places to get back to the user? So it is becoming like an optimization problem, and then we are using RL for that. And this is, one my 10-minute, atomic presentation of Respect for you. Thank you.
All right, thanks, Gökhan again. So we almost have a full room, so we can allow one questions. Please come to the microphone. All right, so I have a question, Gökhan. So in your work, we see a lot of different setting between, using language model as an operation system. But since there's way more text data than the voice data, did you feel is that difficulty to doing the alignment if we coming from voice input to the action execution? Or what's your future perspective on that?
Yeah, future is, of course, spoken foundation models. I think, for a few more years, we will have a separate ASR and language model. But I think it is clear that, Moshi or 11 labs like, systems, will take over. And then, it will be a seamless integration between speech and language modalities. Like in 5 years, this question will be totally irrelevant. And then same thing for other modalities like, image. So image, speech, and text, it will be handled by a single model and in a conversational dialogue. If it is text in, text out, it can be speech in, speech out. You will not think any other option.
All right, thanks, Gökhan. And if you have
you.
any more question, yeah, feel free to post on the line. Yeah, and after this session, we'll have 3 in-person presenter, one from NYU Shanghai, the other from Xiaomi LLM team, and finally will be myself. But now we are really happy to welcome Andreas, who in the EMNLP for a long while, and he will give a historical to advanced perspective on speech and language models. Andreas, please.
Okay, can you hear me and can you see my slides?
Yeah, we good.
Okay, great, great. Okay, so yeah, so this is the second part of the tutorial, and I will be actually diving back into history as the others have done, but at sort of a lower level. I'll talk about language modeling from sort of the beginnings and then how it has been applied to speech processing in particular. Oops, and now I need to make sure I can know how to. Okay. So yeah, so beginning is sort of basics of language modeling, how they have been applied or used to be applied to ASR, then go into neural language models, use of long context, and then working up to the current generation of language models, which of course we're all familiar with and are so happy to use, which is, you know, the GPTs and the other, you know, large language models. And there, in order to actually apply these to speech processing scenarios, we have a number of options. We can use them as post-processors, which is what first was tried. And then we can actually augment language models from text-based to multimodal, meaning speech and text. And that allows a whole bunch of new applications where we do things like speech transcription or corrections of transcriptions, slot filling, summarization, and so forth. Okay, so let's go back to LM basics and some history. So two classic papers here. So it actually started all the way with the Foundations of Information Theory by Claude Shannon. He talked about language models at the character level. He did things like estimate the entropy of English by basically predicting individual letters in a stream of text. And then later, the lead research group at IBM started using what we today would call token-based or word-based language models in the form of n-grams. So the basic sort of, as of, I would say, 20 years ago, the basic state of the art is that you would try to estimate the prior probability of a sentence occurring, meaning a sequence of words. You would do that by applying the chain rule, so you factor it into conditional probabilities. Then you make some approximations by only considering the last k-1 words to basically have a kth order Markov model. And then you would make a further simplification by saying, okay, we'll just count the occurrence frequencies of these word combinations, of these n-grams, and you just you know, estimate by basically ratios of counts plus some machinery to make sure you actually give some non-zero probability to any possible sequence, and that's called smoothing. And then you can apply these models, which estimate prior probabilities of sentences by doing, for example, in speech recognition, you have a prior probability of some word sequence being heard, corresponding to the speech that you heard. And that's combined with what's called an acoustic model, which gives you the probability of seeing the observed acoustic events, given that those were the spoken words. And similarly for translation from, say, you know, Hindi to English, you would have a prior probability of, you know, having, oh, I think I messed that up. So you need the prior probability of English, of some sentence in English, and then you need the conditional probability of the words in Hindi, given that that was the meaning in English. And so you use these language models as components in larger systems where you have something like a noisy channel model to perform decoding of the desired output. Okay. Then specifically now about to apply this to ASR, people came up with a very nifty and flexible scheme called rescoring. So basically, it's not feasible often to use a full large language model directly in the search for the best hypothesis. So instead, what you do is you have some quick and dirty language model, maybe a small language model, maybe only something like a bigram or a trigram language model. And you generate the top candidates for recognized word sequences. And then you apply your big best language model in a second pass, which is called the rescoring pass. And then you apply, and you may even have multiple language models. So maybe you have one language model that is good for, you know, conversational speech, another one that's good for written language and so forth. And you can mix them all together by having this weighted combination of language model scores. And these weights, they're optimized on development data to get the best possible results out of them. So basically, you have your acoustic model probability here first, and then you have a weighted combination of language model probabilities in the log space. Okay. Now, when I was much younger and more energetic, I actually wrote a language modeling toolkit called SRILM. That was it's open source. You can still get it. And it basically did all these sort of standard things that you needed to do to use LMs, mostly based on n-grams, so n-gram LMs and various variants, and apply them to standard things like rescoring and best list lattices, interpolating two LMs to get a new LM, basically a smoothing method, pruning LMs, because you can build a large LM from a lot of data, but then you need to shrink it into something small to fit into your memory and so forth. So all these algorithms, they're implemented there, and you're welcome to use them. But the language modeling techniques that are based on n-grams are now, of course, superseded by these neural methods, which I'll get to in the future, in the rest of the talk. So how do we get to neural language models in the first place? And the very first kind of breakthrough was this work by Joshua Bengio and colleagues. They realized that you could actually use a feed-forward network that essentially implemented an n-gram estimator. So you gave it one-hot encodings for the last, n or k minus or n minus 1 words. It would have a lookup table, basically a lookup matrix that mapped these one-hot vectors into embedding vectors. And that's very crucial. And then you concatenate all these embedding vectors and you have a big feed-forward computation, could be one or more layers. And then in the end, you have a softmax to predict, again, in a one-hot fashion, encoded the prediction for the next word. Okay, so it's basically a neural version of an n-gram model. And the really key, I would say, breakthrough here was that they realized that you can learn these embedding vectors simultaneously with the prediction task. And what that gives you is that it actually, it learns to encode the words in a way that reflects the similarity for the purpose of word prediction. Okay, so you're simultaneously learning the similarity space of the lexicon of your language and the prediction task. And the two, of course, interact and influence each other. So that was sort of the first approach. Then the next thing was to surpass or overcome this limitation of only the n-1 last words. People started using recurrent neural models. So basically, you had a context vector that was a hidden, basically the hidden state of this feed-forward network. But you would save the last hidden vector or hidden state, and this could be multiple, could have multiple levels. But in the simplest version, of course, it's just one hidden vector. And you would essentially make it, you would store it away and make it available to help you in predicting the next word. So the activations would actually flow through time and be, at least in principle, available, for an unlimited history. So this idea is actually ancient. It was first proposed by a cognitive psychologist named Jeff Ellman at UCSD back in 1990. But then it was kind of dug up again and made to work for actual language modeling tasks in at scale with speech recognition and so forth by Tomasz Mikolov in 2010. And this had a very nice, worked great. So he showed that, for example, here in this little table, so these are perplexities. So with a 5-gram model, this is sort of the old technology, you got the perplexity of 94. Then if you use the Bengio, feed-forward approach, you would get 85. If you switch to a recurrent network, you go down to 80. And if you interpolate the traditional n-gram with the recurrent network, you take another step down to 74, 73, 74. So this was really made these recurrent networks very, very popular. Later, this technique was improved further by replacing the simple recurrent network with long short-term memory recurrent networks, which have this memory gating mechanism, and it gets better. It has a better it learns more effectively to preserve or discard information from the far distant past in this temporal unrolling of the activation flow. And that was the state of the art for a long time. When we had this work at Microsoft in 2018, where we beat basically the human transcriber at switchboard recognition, we used these types of language models, essentially. Back then, that was the best we could do. Okay. And another thing that you can do with these things is because once you have LSTMs or some other mechanism of recurrent network that effectively learns from very long histories, you can encode not just one sentence at a time. So you're not just predicting from the words that precede the current position in the current sentence. You can actually feed it the entire conversational history. And on top of that, you can give it both sides of a conversation. So the interplay between two people talking to each other and picking up on the words that the other person used, things like lexical entrainment. If someone has heard about this is what it is. You can feed all that information, and adding the whole conversational session lowers the perplexities, as you can see here. And then when you add information about speaker change, you get another little boost. And if you encode whether the people talked over each other or just talked in sequence, that gives you another little boost. So all this information, this historical information in the context of a conversation actually helps a little bit. Okay, now we get to large language models. Okay, so what's the next kind of big step forward? So basically, it's this neural architecture called transformers that was proposed in 2017 by people at Google. It's a self-attention based layered, multi-layered architecture called transformers. And beyond that, it's not that different from what you saw before. So you still have basically a feed-forward n-gram LM with a few added, twists, namely that we now use much longer context. So instead of using only the last, I don't know, up to maybe 10 tokens, we go all the way out to, thousands or tens of thousands of tokens in the context. We add many more layers, so this could be 10 layers, 20 layers, what have you. Again, the computation is not just feed forward, meaning weighted combination of the previous activations and so forth. No, it uses this self-attention mechanism, which makes it much more efficient to learn interactions between co-occurring occurrences of features in the input at a distance. Okay, that's the hard part to learn, and the self-attention mechanism kind of primes the model to learn these long distance relationships between co-occurring things in the input. And then instead of words, we now go with this automatic decomposition of words into the subword tokens. And of course, tons and tons more data. Instead of using maybe tens or even hundreds of millions of words, we're now talking about trillions of tokens or more. Okay, and there's two main architectures that use this type of approach. One is bidirectional modeling that was actually historically came a little bit before, these so-called BERT models. And then these strictly sort of unidirectional causal autoregressive models, which is the GPT family of models and all the the other big language models that are around today. And we'll talk about these briefly in turn. So the BERT models, they basically each position in a sentence, each layer can look both to the left and to the right. The training criterion is to fill in masked tokens from the input. So you take out some tokens from the input and you ask the model to fill them back in the output. And also there's a next sentence prediction model, which essentially makes the model predict whether two sentence embeddings that occur next to each other actually occur in that sequence in the original text. And what this does is essentially teaches the model about cross-sentential coherence and sentence level basically meaning. And this is not strictly a language model, but it was very, very influential because the sentence embeddings that are computed by these models, they can then be fed into downstream tasks such as natural language inference and tagging and all sorts of sort of speech or language understanding tasks, and has been a real boon for many, many NLP tasks. But the, let's say, more influential architecture currently is the other one, which is unidirectional, where you have a transformer model predicting in a causal manner, so using only things that occurred before in time to predict the next token. The real utility, or the thing that makes these models so popular, is that people found out that you can pre-train these models simply to do word token level prediction as a pre-training step, and then you can very effectively, so this is essentially self-supervised because you just use running text. You don't need any additional annotations or supervision. And then once you have this pre-trained model, you can fine-tune it, meaning using small incremental additional parameter updates to perform a number of other tasks. And the main task that that people train these models on, so we have the pre-training step using massive amounts of data because it doesn't require any additional annotation. And then you have an instruction tuning task where you actually pair inputs with desired outputs. So this is a supervised training task. And often is of the nature that you basically give the model instructions as a context, and then you give it the desired outputs. So this is a supervised task, usually using cross-entropy as the loss function. And then you often add another fine-tuning step, which uses something like reinforcement learning. The difference here is you don't just give it the desired output, you actually tell it not just, you make it learn not just from the good outputs, but you also present alternative outputs, and you actually discourage the model from generating the bad outputs. So you have positive and negative samples essentially, and you're tweaking the model parameters to have a higher propensity to generate the good outputs and a lower propensity to have the less desirable outputs. And there's now many, many different ways to do this. Originally, there was this so-called reinforcement learning from human feedback. Then we had, these are all called preference optimization. So there's a DPO, direct preference optimization. There's now there's things like reinforcement learning from verifiable feedback, and so there's all sorts of from verifiable results. So there's all these sort of slew of proposed way to get this reinforcement learning perform additional tweaking of the parameters. Okay, so why is everybody so excited about LLMs? Well, it's essentially because the pre-training makes it very easy to incorporate vast amounts of both linguistic and world knowledge, because the world knowledge is reflected in the linguistic data. So you learn how to use language, but you also implicitly learn something about the world, and you can bring that knowledge to bear on all sorts of interesting tasks. The use of very long context is of course very, very important. People have found ways to actually feed other modalities, not just text input, and I'll talk about that in a minute. And so essentially, you can treat natural language now as a programming language, because you fine-tune the model to perform instructions that are given not in some formal language like Python or Lisp or what have you. No, you can actually use natural language for programming your systems, which expands the accessibility and usability of these models, by orders of magnitude. And then there's also things like in-context learning. People have shown that these models can actually replicate patterns that are provided not at training time, but actually at runtime as part of the input. So they basically generalize from examples that you give as part of the context and apply them to new inputs. And that, of course, opens up new possibilities because it doesn't require parameter tuning. Okay, so how can we apply this to speech? And yeah, I think we're good. So the oldest way to do it, of course, is just as a pipeline. So we can have maybe an ASR system that generates transcribed speech, and then we apply the LLMs to do something with the transcribed speech. I'll give a few examples of that. You can augment these models by using both the textual information as well as some aspect of the acoustic information as well. And I'll give some examples of that. And then the latest, and I would say current paradigm that people are very excited about is LLMs that are pre-trained with text and then adapted to also operate on speech. So you're trying to leverage all the text-based knowledge and extend that knowledge to a world where you also provide speech as another input modality. And I'll give examples of that. Okay, so I'll just give a couple of examples of LLMs for ASR post-processing. So back when Huck was at Amazon, he came up with this crazy idea of just using LLMs without any fine-tuning and just doing all sorts of very clever prompting to fix the output of ASR of speech recognition. Okay, and he had different schemes for that. I won't go into all the details. In fact, for reasons of time, I'll just maybe focus on one set of it. So this was a typical prompt. So this includes a bunch of instructions. Then it has an example for what you want the model to do. This is basically, this is this in-context learning that I spoke about earlier. And then you finally give it the payload, and then you make it generate, like a fixed hypothesis or a fixed in-best list, and you see what it does. Okay, and here's an example. You have here some speech where there's a company name that's it's a very rarely observed name, so the ASR system has never seen it before, gets it wrong. But of course, the LLM has seen it because LLMs have seen a lot more data, and it actually figures out that this, that this misspelled version of the company name really refers to this company name, and that is the correct answer. And the error rate goes from something substantial to 0 in this case. So this is an example of what you can achieve with one of Huck's methods. So you have an n-best list that originally has something like an 8% error rate, and it goes down to below 7%. Okay, and of course, the larger the LLM is, the better the result, as expected. Then there's another example. This is another scheme that he used. So this is this is an interesting one because the n-best list, again, there was an input coming from the ASR, which was in the form of an n-best list. And this thing called, this is, of course, the first pass one best. That's the error rate up here, like almost 12% for Wall Street Journal, almost 9% for ADIS. And then there's this thing called the oracle error rate, which is the error rate that you get if you pick the hypothesis, magically pick the hypothesis from your n-best list that has the lowest achievable word error rate, okay? So in this case, it was 9.8 and 6.4. And the interesting thing is that with this LLM post-processing, you actually go below the oracle error rate because you're allowing the LLM to change the hypotheses and fix the errors. So it can generate new hypotheses that do not occur in the original n-best list, but are better than the original ones. And you get down to below 9% here. Which is below the oracle word error rate. Okay, let's skip that. Okay, and then Huck took this sort of to the next level. He said, okay, why stop at just ASR correction? Okay, let's do other speech-based tasks, such as when you have a multi-speaker stream of audio, you want to not just transcribe the speech, you want to actually say, oh, this is speaker 1, this is speaker 2. So we have a speaker labeling task on top of the speech recognition task. And then you may want to do things like emotion recognition. So you want to put labels on the speech. Okay, speaker is happy, speaker is angry, and so forth. So Huck thought that LLMs are so smart and they have so much subtle information that can be derived from the speech, not just from the one best hypothesis, but from the whole collection of hypotheses coming out of the ASR, that they should be able to actually improve these post recognition tasks, okay? And he set up a challenge at the competition, a benchmark, a bake-off at the last SLT workshop, so about a year ago, where people competed on these tasks. He assembled a corpus of best outputs from different ASR systems for different types of speech. And there's a whole special session from the workshop and papers and so forth. And this is one of those things that you can push this technology to. But this is all just based on textual output, right? So we're throwing away the audio. We're simply encoding. We're only using the ASR text strings that come out of the initial recognition. Okay, let's go beyond that now. What can we do if we add acoustic information to the text-based information and then use LLMs to operate on it? I'll just give you two examples. And these were both intern projects at Amazon when Huck and I were there. One thing is that there's this thing called sentiment or emotion, where the same string of words can actually have multiple interpretations depending on how it's spoken, right? So for example, someone could say, I watched a baseball game during the weekend in a neutral tone of voice. And then the conversation goes along, and then there's a response here saying, oh, the game wasn't bad, and it could, but the tone of voice says, oh, I was not happy with the outcome of the game, okay? Or you could say it in a way, oh, the game wasn't bad, and that conveys a positive sentiment, right? And then the appropriate response, of course, would be vastly different. If I'm an empathetic listener, I would pick up on the fact that maybe here the speaker is not happy with the outcome, and here they are, okay? Okay, so in other words, what comes next in a conversation is very dependent, not just on the words that were spoken, but also the sentiment that is conveyed with the words. And that is conveyed partly by the acoustic properties, such as the prosody, the intonation, and so forth of the speech, okay? So we built a model that actually not just predicted text tokens, but also predicted emotion labels or sentiment labels in this case. And the way in which this worked was that you had a word history of the conversation up to the current point. The model would predict the sentiment of the last sentence. Then it would predict the sentiment of the next utterance. And then it would predict the words of the next utterance. So essentially, it's a language model that now operates not just on word tokens, but also on sentiment tokens, okay? And we found, and I won't go into there's too many numbers here, so I'll just give you the gist of it. So of course, the sentiment was conveyed partly by acoustics, which is why we fed these embeddings from a speech encoder into this model. Okay, so we augmented the language model to also take in these embeddings that represented acoustic properties of the last utterance. And of course, the sentiment modeling, the sentiment prediction was improved by giving this acoustic information. That's just what you would expect. Then by having these acoustic information, you also improve the text prediction, okay? That's interesting because it means that for good language modeling, you actually need more than just language. If you're dealing with speech, you need the acoustics as well. The textual context, of course, is very important. It's the main conveyor of information. And also that the contextual speech embeddings and the sentiment of information, they're not redundant. They contribute independently to the quality of the output. So by using both, you get the best possible results. Okay. Another example of a acoustically augmented language model is this work by another one of our interns back at Amazon in 23, published in 24, where we try to predict not just the words, but also when it is the appropriate time to either keep listening to what the other person is currently saying, or to jump in by starting your own turn in the conversation, or by issuing something which is called a back channel, where you're not trying to take over the conversation, you're not trying to take the floor, but you simply want to signal that you're listening. So these are called back channels. In English, there are words like uh-huh, yeah, okay. Those are words that are called back channels. And so we modified an LLM to predict the appropriate locations in the conversation where you would do one of these three things: keep listening, back channeling, or take over the turn. Okay. And we augmented this by an acoustic predictor, and then there was here the integration was done differently. Instead of feeding the acoustics into the LLM, we had a fusion model, a very simple fusion model that just combined the prediction of both the acoustic model and the LLM. And this was quite successful. You can, okay, I won't try to explain details, but basically what this shows is that the model learns to back channel when the other person is at the end of a sentence, right? Because that's the opportune time to say, uh-huh, yeah, because it signals that you've actually followed what they said, and that's where you signal that you've listened and that they should keep on talking. Okay, so the back channeling, if you do it in the wrong place, it's very it's kind of it makes you uneasy because it means the person isn't really listening to you. But this model learns to do it in the right place. Okay. Okay, so now finally we come to the speech LLMs. So speech LLMs are essentially LLMs that are turned from single modality, meaning text-based LLMs, into multimodal or bimodal LLMs, meaning you have a text modality. In addition, you have a speech modality on the input side. Okay, and the way and the idea is that you can feed the LLM some text tokens, followed by some speech embeddings, followed by some more text tokens, and in particular, you can feed it instructions on what to do with the speech information, right? So you can instruct it to say like, oh, transcribe this utterance, or what language was the utterance, or what was the gender of the speaker, okay, or what was the translate the speech into another language. So the idea is to basically have it be instruction following and perform all sorts of speech-related tasks in a single model potentially. Okay, that's kind of the ultimate goal, and of course we're kind of building towards that. We're not quite there yet, and the rationale for doing it this way is that by having the pre-training on these gigantic amounts of textual language, you hope that the model learns a lot about language in general and all the world knowledge and so forth, and then you just give it that little bit of extra information to help it map speech to the equivalent in a textual representation. Okay, so how do we do that? Well, one architecture is, by the way, there's a survey paper, there's different ways, different architectures and so forth. We'll just talk about one architecture depicted here. Basically, the idea is that you take an audio encoder that was pre-trained on some ASR-related task, like you have an existing speech recognition system, and it has the early stages of that model basically do an audio encoding into some kind of frame-based embeddings, for example. And then you have a specialized projector or adapter model that maps these audio embeddings into the embedding space of the text-based LLM. Okay, so you learn this projector, and while doing that, you keep the LLM at first frozen, which forces this audio front end now to basically adapt to the knowledge or the input representation of the LLM. And that's crucial because you want the LLM to keep being able to use all its pre-existing knowledge, right? All its pre-trained knowledge. And there was one particular model called SLAM ASR where they did this in a particularly kind of simple way, where the projector was just a single layer, essentially a single MLP, feed forward. The audio encoder was from a pre-trained acoustic model called a WaveLM, and to match the time resolution of a speech representation, which is frame-based, every few tens of milliseconds, you go to a text-based representation where each token represents, maybe maybe half a second or a quarter of a second. So to match the sort of time scales, you do a downsampling between the audio embeddings and the tokens that you want to be feeding to the LLM. So you do this by downsampling. And this model was surprisingly good at doing speech transcription, although it had some limitations, which we explored in an ICAST paper earlier this year. But still, this stuff actually works, which is surprising. And you can do other things. For example, remember the post-ASR correction that Huck worked on early on? Well, you can actually do that with a speech LLM where you feed it multiple transcriptions for a piece of audio, for an utterance. And then you also feed it the audio embedding. And you let the LLM or the speech LLM now resolve which of the transcriptions is the best one, considering what the audio embeddings were. So you give it information about, basically it's a critic of the different ASR systems in light of the original audio input, and then you have it output the best transcription. And the results here were quite striking because we used this for unsupervised training of ASR models. So we needed basically to replace human transcription with automatic transcription. And using the scheme, we achieved even better result than with human transcription, right? So this system was effectively more accurate than human transcribers in generating large amounts of transcribed speech. Sorry, in generating large amounts of transcription for existing speech. This was a paper at InnerSpeech earlier this year. Okay, next application is, this is work by my colleagues Kadri and Manjanath. They explored whether you can do slot filling. This is zero-shot slot. So what is zero-shot slot filling? It's where you have essentially an open-ended class of the possible set of slots that you want to fill and recognize and then extract the information for is open-ended. So, you don't have, half a dozen types of slots and you've seen them all in your training data. No, you want these slots, they could be something that you've never seen before. So you give it a list of the slots, but these might include slots that have never been seen in the training data. And this is very common in industrial scale applications of AI, where you want to extract information that could be very domain specific. And you simply need to use your human sense of what it means, like the slot is maybe, I don't know, savings account number, okay? Okay, maybe that's not so rare, but you could see a slot description that means something and but has not been seen before. But you can make sense of it. It's probably some string of numbers, and you can make sense from context where the slot occurs in your input data. So this is zero-shot slot filling, and what Kadri and colleagues did is they you prepare a corpus of speech utterances that have these slots, and you look at how accurately can you extract these. You measure this in terms of F1, and you have the in domain where you've probably seen most of the slots, and then you have the out of domain. And you can either do it with a pipeline of a standard ASR system like Whisper followed by an LLM, or you can do it in one shot, essentially with a speech LLM, where you feed it the speech signal, embeddings for the speech signal, and then you instruct it to extract the slots. And you can see here that it's you actually achieve results that approach the best what you can, or even surpass the best of what you can get with a pipeline system if you have one of these pre-trained multimodal speech LLMs like Qwen2 Audio. If you don't have a pre-trained multimodal LLM, then it's difficult to achieve the pipeline system performance, but you're getting close. So here, for example, you get close, 0.55 when the pipeline system gets, 0.64. So I would say it's not a solved problem. It still needs to be improved, but it's getting there. Okay, and then finally, this is also work by Kadri and Manjunath, hot off the press. This is kind of the equivalent of chain of thought for speech LLMs. So if you want to extract information or do some kind of, be it slot filling or translation from a speech LLM, it stands to reason that you could actually improve the result by doing the processing step by step. In other words, by prompting the LLM to first generate a transcript of the speech and then the desired output, the semantic output, the interpretation output. And that's exactly what they did. They trained an LLM, a speech LLM, first of all to to do the task, of course, but as a secondary task, they also trained it to produce an intermediate result, which was the transcription of the speech, and this improved the performance. And this is you have this sort of output that includes a sort of thinking portion where you see sort of the intermediate results being displayed before it comes to the final response, which is the slots and their fillers. Okay. All right. So concluding now, so LLMs are very, very useful for ASR or speech processing in general. We started out by just doing it as a post-processing step. Then we have several successful attempts to augment the LLMs with very specific acoustic information to do things like turn taking or sentiment labeling in the prediction step. Or we now arrived at the point where we have bimodal LLMs that understand both text and speech on the input side. And there's still many techniques that we can presumably develop to make this work better. There's a lot of open problems. For example, we keep developing new training techniques, such as this reasoning, prompting to reason, to surpass the state of the art in terms of pipeline systems. We are trying, there's some ongoing work that's I can't talk about yet, but we actually applied reinforcement learning to speech LLMs for certain tasks, and it helps. There's a big question of how to most effectively combine text data and speech data, and especially when it comes to out of domain, when there's some kind of mismatch involved between either the domains or the acoustic properties of the speech involved. And finally, these models are very computationally expensive. You can imagine that the contexts get longer and longer. By having speech as input, the contexts get even longer. So there's a great need to come up with computationally efficient models, reduce latency and computational demands. Distillation techniques, different so-called small language models applied to the speech LLM domain. So these are all things that still need to happen in order for these models to be, I would say, computationally viable. But it's an exciting field, and we're seeing more exciting work every month or every week. If you're on the archive, it's amazing all the stuff that's happening. So I'm very hopeful that we will that great things are still to come. So that's it. So any questions? I'm a little bit over time, maybe.
All right, so let's thank Andreas again. If you have a question, please go to the stage. Yeah. We have 3 questions from the in-person audience.
Okay.
Thank you very much for the tutorial. It's very great, very good. So I have 2 questions. The first question, can you comment a little bit about how you generate the training data to train the adapter? And my second question is for multimodal large language model. It partially started with training the adapter for the multimodal input. And later on, the new architecture, much more of treating the multimodal input as first-class citizens. And do you see that will happen for speech LLM as well? Thank you.
Sure. So So the problem, of course, is the availability of data. So the text data is so plentiful and so easy to come by that it's hard to generate an equivalent amount of speech data. That's why these models, bootstrapping them from the text modality is so attractive. How do we get this? So we do need the paired data, it's speech and the transcriptions to do the adapter training, as you say. Well, we can use the traditional corpora that we already have, of course, the same corpora that we use for ASR model training of the traditional kind, we can use for the adapter training. And we can also use data synthesis methods. So we can use TTS systems, for example, to generate speech that corresponds to existing text data. So that's a technique that's been used for ASR for a long time now, and we can use that here as well. And yeah, so making speech first-class citizen, I mean, again, it just boils down to the availability of data. I mean, as we get more and more data, maybe we no longer need text data. I don't know, but I think there's still there's orders of magnitude difference between the available text data and the available speech data. So I'm a bit skeptical that we can get completely rid of text data. Other questions?
Hi, next question. My question is more about so the tasks you described were mostly ASR and slot filling, which are mostly semantically semantic tasks regarding the utterances.
Yeah.
I was wondering if there are works regarding speech LLMs and acoustic properties of speech, because
Yeah.
about
So
how
so
voice,
we are working, and I think there's some other work also on emotion from speech. I already talked about the speaker labeling task or the speaker boundary detection task. We have not worked on that, but I'm sure someone is. I mean, the easy ones are things like, language ID and gender ID and so forth. So I don't have a full, full knowledge of every possible thing that's been tried, but that should be a fairly easy task for speech LLMs. These sort of, low perplexity classification tasks should be fairly easy to do with speech LLMs.
Actually,
Okay.
I was wondering,
Yeah.
because, well, a lot of the speech LLMs use high-level semantic representations from existing audio encoders, like maybe a Whisper or WaveLM or WaveT. And since those are also mostly especially like Whisper, those are mostly trained on ASR tasks. So
I see.
they might
So
be
you're wondering whether those pre-trained acoustic embeddings are suitable for the other tasks that are not for transcription. Yeah. That's a good question. So you can always fine-tune them, right? So that's something that's still an option. You can unfreeze the encoder, the acoustic encoder. But these embeddings also are quite rich. They do encode. I mean, you would think that they maybe strip away all the non-lexical information, but that's not actually the case. So there's still a richness of information in these acoustic embeddings that can then be picked up on in the other tasks that you're interested in.
Okay, thank you.
Sure.
All right. We can have our last question. Yeah, go ahead.
Thank you for your talk. And do you think that the speech could be injected into the text language model during the pre-train stage or continual pre-train stage? And next question is do you think speech language model worth to scaling up to the 200B or 300B? Since we are currently only have model right now.
Well, there's already, audio text models, bimodal models that are pre-trained on both modalities. There's the Qwen2 family of models, and there's the 5.4 family of models from Microsoft. So those actually, those models, if you can use those as your starting point, they actually improve performance quite a bit, we found. Whether they can be scaled up to very large model sizes, I don't know. I mean, we actually have some limitations on the size of the models we can use. I mean, others have other limitations, I'm sure. But on the training side, I'm not sure. I don't think there's an inherent limit anywhere. It's just a matter of compute resources and data availability.
Thank you.
All right.
Okay.
One comment. So Andreas too humble. A lot of work. I'm working with him is like all my ASR knowledge has been educated by him, and that was interesting. 3 years ago, we jailbreaking the like instruction GPT for correction. Yeah, and
Yeah.
I think he also have some words about you can see this year for voice language model, the industry and interest is coming back. Maybe he also have his own unique opinion, but if you have interest, feel free to connect with him. Due to the time issue, I'm really happy to introduce our next invite speaker from NYU Shanghai, Professor Hua-Shen. So Hua-Shen did his PhD at Penn State, and later on took two postdocs in UMich and UW. And her research area is between HCI and voice, and especially on the value alignment. So she's recruiting also if you are an undergraduate student.
Yeah.
Yeah. Go ahead, Hua.
And can I just say one word? So I'm especially pleased to have Hua here as our speaker, because not only did I have the privilege of working with her when she was as an intern at Amazon, but she also just received the Best Paper Award with her colleagues in the main conference. So fantastic work. Take it away. I'm going to stop sharing.
Thank you so much, Andreas. And thank you so much, Huck, for the amazing introduction. And let me share my screen. I hope everyone could see my screen and hear me clearly in the Zoom, right? Zoom, good. Okay, awesome. Hello, everyone. It's really nice to meet you. Really appreciate this amazing opportunity. I feel really honored to attending and supporting this amazing tutorial. And my name is Hua Shen. I actually just joined the NYU Shanghai as assistant professor of computer science in this fall semester. And I just graduated from UW and previously the UMich as a postdoc. And I am very excited to introduce a unique perspective from the human-centered views and some contributions to improve the spoken LM and spoken conversational agents work. So I'm happy also to take any questions, or feel free to stop me if you have any questions. And so today's talk, I'm going to talk about towards human-centered alignment in spoken language models. And specifically, we know that the speech LLMs are increasingly integrated in our lives, such as the voice assistant devices, the speech-to-text transcript services, and accessibility for disabled people. So they are making more and more impacts for the real-world society. In the meanwhile, we also know that the human-centered alignment is very crucial, not only on the performance base, so that we need potentially some human-in-the-loop feedback or preference, like Andreas also mentioned, the RLHF, DPO, those kind of algorithms to improve the spoken LLM algorithms. On the other hand, we also need the human's perspective to ensure and improve the responsibility and safety values that make the spoken conversational agents truly helpful and trustworthiness to the end users. And also, it's important to empower or help the humans to better understand and collaborate in the future real-world scenarios, like the home assistance and the smart home, etc. In the meanwhile, we are facing a societal challenges today due to the misalignment between humans and AI. And you might be wondering, oh, what does this mean and what is resulting in? So human AI are not fully aligned in nowadays so that we can observe the privacy concerns of voice assistant and also the stereotypical biases in the voice assistant as well. And there are many negative impacts on the children when they are using the voice assistants. So given this, responsible and reliable AI for society relies on the effective alignment between the humans and AI, and especially the spoken conversational language models. So let's see. Okay, we just finished our introduction, so it's a great pause, and we can wait. Yeah.
Yeah, the underlying team just arrived, so maybe we just need 2-3 minutes to back to the screen.
Yeah. And it's great. I think all the previous speakers are having amazing talks with intensive knowledge. So it's also a great, like a small break for us to relax and then see some novel perspective from human side. Yeah.
Yeah, for the online audience, we have some issues about the local screen. So, all right, so seeing some connection issue. All right, Larry, Andres, are you still online? Can you hear us? All right,
Yeah,
maybe
I can
also
hear.
Gold.
I can hear, yeah.
Yeah, I can hear also.
And I see a screen. Would it help if one of us shows the slides? Although I actually can't because this is not in PowerPoint.
I guess they are fixing the on-site screens, so we can just wait a bit. Let's see. The Zoom seems it looks pretty good.
All right, so the projector is overheated, so let's have a 5-minute break and come back. Yeah. So sorry for Hua and people online. Yeah. Hua, can you also tell the online audience we gonna do the 5-minute fix? Yeah, in the Zoom.
Too much hot research.
Yeah, yeah, yeah. Can you hear me, Andreas?
I can hear.
Oh, yeah, great. So we will have a 5 minute break
Yeah.
because the machine is overheated. So we just break a little bit, relax a little
Okay.
bit, and come back 5 minutes later. Yeah. Thank
All right.
you.
Yeah, something else. Turn it off.
Do you need yeah, and it's only, I think the Zoom works pretty well, and it's only these like a little bit. Oh, yeah. I'm go, it can, if I identify that. Thank you so much.
Still black background. No, no. Then it should display. Yeah, it's already displayed.
Well, you visited UD4 office 2 days back and I work in this hospital.
Yeah, I visited his office actually this summer, and it's really great. It's in Palo Alto.
Yeah.
And yeah, we are like, I am also supporting one of his workshop in ASRU this Hawaii, like this December. Oh, really? Yeah.
Yes, sir. It's like in US.
I clicked the
In ASRU Hawaii this year. Is that the one?
Oh, is it US?
Yes.
In US.
US, yeah.
Yeah. So I think they have some like visa, they couldn't join it in person in China, but yeah. Like that ASRU conference is happening in December 6th. And especially Andreas workshop, and I am also flying to Hawaii supporting his workshop as well. Yeah. So yeah, are you also work?
I work on the with Andrea.
Yeah. Oh, so you're also in Palo Alto
No,
office?
I'm in Bangalore. Yeah. We have
International offices.
yeah. India, there are many.
Yeah. That's super cool. I visited your something like a Palo Alto office, so which is very nice. Yeah. So yeah, it's you have international like a team located in India, US.
Started in India.
Mm.
Then started like West India.
Oh.
And then we have
Europe.
in Europe.
Oh.
Many places. Initially we had in Japan, but we just closed it.
Switch to 2HDMI in the fiber.
Nice to meet you. Thank you so much.
You pull the DVIs out of fiber and switch them.
It works. We got it. No, we got it. It works.
Can online audience hear us?
Yes, we can hear you.
Okay, so let's restart. Yeah, sorry for that. Like the 5-minute like technical issues. Like Huafar NYU Shanghai keep going on speech and AI. Yeah.
Great.
All right. What can you play?
Yes. Let me see whether I can go next slides.
Oh, back to the Zoom screen for local one, right?
Awesome. Okay, thank you so much for your patience, and thank you so much for like it's I think the machine is like the brain of the machine is like maybe mind bloated with so many like knowledge. So it's a great time for relax, and let's come back. And it's also a great time for the small pause because we are gonna to introduce the true research projects for today's talk. And since we're working on alignment, and especially I have some like experience in human certain perspective. So for today's talk, I'm gonna talk about the speech LM related tasks regarding these three components. You can see one is human, one is speech LMs, the other one is textual LMs. So they should all align with each other. So that's why you can see there's alignment in the middle of this architecture. And between human and speech LM, we need to, or we have some specific relevant tasks regarding speaker tasks. And between speech and textual LM, we have some related tasks such as ASR, speech classification, and regarding some human and textual LM, we have some relevant tasks regarding downstream tasks such as transcription, disfluency, etc. And for today's talk, I'm gonna share with you about some paradigm shifts in the speech LM regarding the very beginning of the fully supervised learning, such as the typical CNN-based speaker models. And then we came to the pre-train and fine-tuning era where we have the BERT-based language models. And then nowadays it's more and more popular to have this GPT-based model. That's why we have these generative speech language models. And I have conducted some research corresponding to these three typical type of paradigms and also relating to these three typical alignment tasks. So I would love to share with you about this. More specifically for today's talk, the part one is about responsible speaker verification models to improve the speaker fairness, where I collaborated with Andreas during my Amazon internship time. And then part two is about human feedback on multi-turn discontinuity to clean up the spoken conversations, where I finished it during my Google research intern. And then the part three is about the speech LM prompting for diverse speech processing tasks, where I collaborated with an amazing speech LM professors named Hongyi Li from the Taiwan NTU. And in the end, I would wrap up and zoom out to seem a little bit look forward, which I'm currently working on value-centered bidirectional human AI alignment. And I believe the spoken LM is playing a more and more important role in this future direction. So let's start with the first part. For this part, this paper was published in ICAPS 2022, named Improving Fairness in Speaker Verification via Group Adapted Fusion Network, where you can see Andres in the last author. And given some background and motivation, the performance of speaker verification system are dramatically improved due to both deep learning algorithms and large-scale data set back in 2022 areas. And the speaker verification models are typically described with two stages, where you can see that the first stage is about embedding extraction, where we usually use deep neural networks to extract the speaker's both acoustic and transcript signals from what they're saying. And then the second part is about scoring functions, where we need to compare two different speakers, embedding and then computing the similarity score to decide whether the speakers are from the same people or from the different people. Well, given this, there are usually two paradigms to train the speaker embedding extractors, since they are very important to conduct the similarity, the follow-up similarity. The two, one is about classification loss, the other one is training as a goal of metric learning loss. And the high-level philosophy or idea about metric learning loss is that when we have different speakers embedding or their acoustic like signals transforming into like these high-level embeddings, each of their utterances will be represented with like a dot in the high dimensional space. And then the goal is that we want to minimize the each speaker's embedding, like basically making them clustered tightly, and then making the intro clustered like far away from each other, so that these optimize the embedding to get smaller distances between the same speaker and larger distance between the different speakers. Well, given this goal, we also observed many more and more issues or problems happening in the spoken-related languages, not only speaker verification, which actually observed from the Amazon like real data, but also more speech-related tasks such as ASR, where, for example, you can see when we consider their demographic information, the black and white related like subgroups are actually performing very different regarding their WER, and there are more and more reports in the news regarding these fair and unfair or bias. So given this, we want to address this problem and analyze what's wrong inside of them. From our initial analysis, we suspect that this learning process can potentially lead to model unfairness in the demographic minority groups from both training and evaluation stages. Regarding training, the model currently are trained to minimize the average loss without or overlooking the fine-grained demographic information during the data. And regarding the evaluation part, actually at that stage or back at that time, there's no evaluation metrics that has such a fine-grained evaluation to detect whether the model are fair regarding different demographic groups. So given these challenges and this analysis, in this project, we aim to present a systematic study to, first of all, examine the model fairness in speaker verification systems and further address this problem by providing a novel method to effectively improve the model fairness performance. So how did we do? And this is the basic idea or model we proposed in this project, where we improved not only their front end, which is the embedding extraction, but also their back end, which is the scoring function. So in the front end, we proposed a group-wise embedding adapter, basically leveraging the idea of mixture of experts, if you're familiar, MOE. And the second one, we actually aggregate all these experts embedding in their scores using this score fusion strategy, basically a weighted sum of all these scores. And for more details, for the front-end one, group adapted fusion network, you can see that we have the base encoder, which was actually generalized used in the, at that time, in many speaker verification systems and also deployed in the Amazon. And then based on this base encoder, which was trained with mixed demographic information, we then fine-tuned with like 2 experts or 2 specific gender-oriented adapter encoder, including a female adaptation encoder and a male adaptation encoder, so that we can have not only the overall demographic embedding, but also the specific groups embedding experts. And then to aggregate all these different base and male and female encoders, we actually extracted this score fusion network, where you can see that we compute the similarity, given the one specific pair of utterance to decide whether they are same or different speaker. We put them in all of these encoders and using a score fusion model to aggregate all the fused scores, so that you can see here is the embedding adaptation outcome and the score fusion models, and we use a binary cross entropy loss to optimize this overall process. And to rigorously evaluate and train this process, we actually also contributed a novel training set and a novel evaluation set, because at that time, there's no fairness gender-related data set for this problem. So what we did was that to train the different gender-balanced data set, we keep all the amount of total speakers exactly the same with 2,500, and then we varied the different ratio of female and male from 9 versus 1, 4 versus 1, 1 or 1, like equally, or 4 versus 4, 1 versus 4, and 1 versus 9, so that we can observe more balanced and more different unbalanced regarding different female and male ratio. Furthermore, we also customize our evaluation set, keeping all the female the same, but have a mixture of female plus male, and even a harder evaluation data set named Voxelab 1 fairness hard that has like this ratio of different female and male pairs, so that it will be even harder to compare between 2 female and between only 2 males. Given this data set, another contribution in this work was we developed this novel metrics for evaluating fairness in speaker verification, based on the commonly adapted or used equal error rate, named EER. So we developed 3 specific metrics, including the group-wise EERs, like female group and male group. Also, the model performance gap, named disparity score, basically their absolute subtraction. And also, we expect the largest EER across all groups to be as minimum as possible. So that given this, here's our results, where you can see this is on the first evaluation data set, and the second one is even harder. Given this, you can see that this is more balanced area with female and male as balanced, where the ER lower the better is relatively the lowest among all the cases. And then when we go with the more female, we'll go with this direction with more male, you can see that the more data when we have, like one female here has 90%, their female's performance would be pretty good. Like this is the line of male, but the female's performance would be really bad. On the other hand, when we have like more female, 90% of female data, training data, and then the female's performance would be truly good, but the male's performance would be really bad. So in short, it means that the more training data for a specific gender we have, the performance would be much better. On the versus, like on the other hand, the rest or the other gender would be like much lower. And so you can see, given identical total training data sets, imbalanced group ratios are actually leads to model unfairness significantly. And we not only using using this overall score to understand what's happening. We also visualize their embedding to want to interpret what is happening in the high dimensional embedding space. Where you can see that the upper part is we do the dimensional reduction within the Tisney projection method. Here is before the our method using just some baseline models. You can see each color means one speaker, and then after using our new method where we proposed the group adapted network, the in between like speakers embedding are much closer to each other. The different speakers distance are much farther to each other. We further quantitatively want to measure this embedding relationship and the names and the values. So we using this Soloid coefficient to quantitatively measure this phenomenon. So so you can see that the score of the Soloid coefficient going much higher, indicating that this performance is actually quantitatively verified much better. Our method is much better. So given that, a short summary of the speaker verification fairness project, we proposed or defined the fairness on speaker verification systems as a new problem, contributed some new data set, a new evaluation metrics, and also a novel method for that specific problem as a solution. Well, given that, let's come to our part 2, which is alignment between the humans and the textual LLM with regarding to some downstream tasks. This task was published, this paper was published in EMNLP 2023, basically 2 years ago in Singapore. And the title is Multi-Turn Cleanup, a benchmark for multi-turn spoken conversational transcript cleanup, collaborating with my Google research collaborators. And in this case, we focus more on like the multi-turn conversations, given the background that the voice AI system nowadays are more and more widely used in everyone's home, like the Alexa AI, Google Home, etc. Inside of these systems, the core models are the ASR, automated speech recognition system, where they transcribed the human spoken conversations with the acoustic signals into the transcript, and then doing the following downstream tasks, such as either capturing in YouTube or like capturing in our Google meeting, Zoom meetings, or actually do some downstream NLP tasks, such as like Q&A, summarization, etc. Well, inside of this part, we also observed from the real-world data that human spoken conversations are very different from the written text. So you can see here's an example of the conversation from the real switchboard data set. When we are writing the conversations, it's more like structured and more neat. But when we are saying or speaking during the dialogue, like Andreas also mentioned, the back channeling, you can see many of these like these words such as yeah, aha, I mean. So these are actually some redundant information that would potentially harms the downstream task in either like a capturing or Q&A. So the goal for our task is to remove these disfluencies or discontinuities such as repeats, self-corrections, back channeling, etc. However, we observed while removing these discontinuities, it's very important to not only ensure the good performance for more speech-related and NLP-related tasks, it's also important to ensure the fairness for some minority groups with speech difficulties or disabilities, such as individuals who stutter or elderly individuals who with speech impairments. So that's why we aim and need to clean up the multi-turn spoken conversation transcripts in this work. Well, there are actually already a large amount of papers, research happening in this field in the past years, largely named the single-turn disfluency task, if maybe many of you are familiar with it. So they usually use either a rule-based method, like you can see that they identify some reparation, interrogam, repairness, etc., or using some modeling trained on some existing data set to remove them using BERT-based model. However, we observe that there's no disfluency or those modeling or method on multi-turn situations. So what does multi-turn discontinuities mean here? So you can see that I'm providing one example here. The multi-turn is not only focusing on single turn, like removing back channeling, but also some of the repetition are actually repeating the same, like the same speaker's last turn. Like the speaker B said, oh, just in the last generation, and then he or she said again, just in the little while, just in the last little while. So you can see they are semantically the same and also a cross turn, but existing models could not identify them and remove them. So we focus on these type of multi-turn discontinuities in this task. However, we found that there's no data set, there's even no task definition, let alone there's no modeling. How could we address this problem from the real world, like Google and industrial needs? So the goal of this project was that we want to develop a systematic approach to define and detecting these multi-turn discontinuities in the spoken conversational transcripts. Well, given this, we actually develop a very systematic approach regarding defining the task based on linguistic taxonomy and the definitions, and then generate a novel data set based on existing single-turn disfluency data set, which is exactly the switcher board, if you are familiar with. And the third one is we proposed two modeling methods to address them and also develop these evaluation metrics for benchmark. To briefly go through this context, to define the task definition, we define the multi-turn spoken conversational transcript based on TreeBank 3, which is a very commonly used linguistic data consortium, and also grounded on the switcher board corpus, which is actually a real human 5-minute conversation, telephone conversation, so that they not only have the original audio, but also have some transcript. And then we define the multi-turn discontinuity actually include not only single-turn disfluency, but also cross-turn discontinuities simultaneously, which means that multi-turn actually are still including single-turn, but actually going a little bit farther. And given this, we needed to collect some novel data set. We targeted or grounded on the switcher board data set, and then one need to hire or have more human annotations on annotating those multi-turn situations. We first of all generated the taxonomy or the definition with 5 different categories, and then recruit the annotators from Amazon Mechanical Turk to do this annotation. You know, having the human annotating these very complex data set is it's a very challenging problem. So we actually specifically, or maybe actually the most challenge in this problem. So that's why we developed these 4-step schema for crowdsourced data annotation on the Amazon Mechanical Turk. More specifically, we first of all have some pilot study to finalize our interface that could allow the human to interactively label and have their comments on the specific annotation or removing discontinuities. And then at the third stage, we recruited over 250 qualified Amazon Mechanical Turk workers to help us and annotate this data set. And this is not even enough because we use the qualification filter or threshold as a F1 score with some ground truth. We annotated among our authors so that we have the ground truth, compare the annotators' responses, and set the threshold as around 0.0 0.6 or 0.5-ish to filter all the like unqualified one. So, and then this is even not enough. We further develop this batch-wise data annotation scaling method so that we actually decompose the overall very large data set into small batches. And inside of each batch, we actually inserted a hidden qualification filter or qualification heat so that every time or every batch, we can filter all those like unqualified worker and their annotation so that ensure the overall process and collected data was with high quality. And so we leveraged the strategy of UI-centered to optimize our user interface, person-centric to collect or invite qualified workers, and process-centric, these three strategy. And then here's our data quality. You can see they have pretty high like quality scores. And also we developed 2 models to do this process, all based on BERT model. And this is, we again use the cross-entropy loss to optimize all these like 2 modeling. Given that we need to improve both single turn and multi-turn across these tasks, we developed 2 modeling process. The first one is 2-stage model, where we remove first and second like separately, where we actually have an overall data set to remove them overall. Well, we are given limited time, won't go through the deeper into these stages, but we can see that the overall results of our modeling are much higher than the baselines. Well, given this, a very quick overview of the part 3, which is speech relevant task, where this is amazing collaborator with many different like collaborators across industrial and academia named the speech prompts. And in this project, we focused on the new paradigm shift on spoken language model using generative or autoaggressive general modelings. So you can see that we are developing this novel way of text-less spoken conversational modeling, composing with different key modules such as unit LM, prompt tuning process, and also this unified speech to unit generation and verbalizer to decode all these either text signals or speech signals. So you can dive deeper into each of these like different modules novelty. And based on a large group of tasks and the modeling setups, we verified that these prompt tuning based or the novel method are actually outperform the baselines significantly. Well, given this part 3, let's summarize and have a conclude. We observed that human-centered alignment for speech-language model to achieve high performance and respond to speech LM should not only focus on the performance, but also focus on the responsible part of these models, such as fairness, values, etc. So given this, we are looking forward and proposing value-centered bidirectional human AI alignment, where we have this bidirectional overview grounded on this like actually survey of Europe's 2025 happening like later in December of in San Diego. We proposed this detailed definition, and one follow-up I just presented at this EMNLP 25, as Andreas also mentioned, was this value alignment inside of a text-based language model. So I believe in spoken-based language models, we also need to evaluate whether they are aligned in their between human versus LM, or whether they are aligned between what they say on values and what they act. And yes, more awareness and actions are needed in our speech community to improve the bidirectional alignment between humans and AI in spoken conversational agent systems. And in this December, I am also supporting Andrea's work in the ASRU workshop in the Hawaii. So we would both attend there in person and welcome, and would like to see you again in that workshop as well. Thank you so much.
Thanks, Hua. Since we're a little bit over time, we can allow one quick question. Anyone? All right, so let's welcome Don from Xiaomi. He gonna introduce Mimo Audio. All right, so I think we still have some buffer time, so the session will be finished around 12:30. So, but if you have more questions and you want to interact with what she's there, yeah, feel free to come to her and chat directly. Yeah. All right. So I'm happy to introduce Dong. Dong now is a principal researcher at Xiaomi large language model core team. And I'm happy when I met him, he was a master student 2-3 years ago. And yeah, and Dong gonna introduce the recent work about open source MIMO audio for about 10 minutes with 5-minute talk. Is all yours, Dong.
Yeah, thanks Hank for inviting me here. And today, I want to share our recent work MIMO audio, and which showing that audio language models are few short learners. And I'm Dongzhang from Xiaomi M core team. So, okay. So first let's ground this. What should speech LLM pre-training be like? And this is the core problem we are talking with and in our MIMO audio paper. And this is how Ilya described what is text LLM pre-training doing. And he says that when the language model predicts the next word, it's not just learning the statistical correlations in text, but it learns a word model by compressing the text corpus very well. And the language model is learning the people, the human conditions, and their hopes, their dreams, and motivations. So I think a speech pre-training should do similar things, and it should build a speech word model, and it should learn how people express themselves and with different background and different emotions, and yeah. So I'll describe the speech LLM pre-training and into three key steps. The first is unsupervised learning through compression. And the second is that when we scaling this, and the model will extract all the hidden scripts and patterns in the data. And finally, it can generalize, and it can do more than repeat what it has seen in the pre-training data. It can generalize, like future learning and like something like that. And let's see how current speech LLM perform next speech prediction. And I think one common approach is the thinker-talker architecture, and the thinker converts the speech into text, and the talker converts the text into next speech. And there is a stop gradient here. And so for this, the thinker is the LLM part couldn't directly learn from the speech signals. So I think which also limits its performance. And the second approach is LLM plus diffusion or flow matching method. So the language model part predicts the lossy speech tokens, which is usually from a whisper representation. And there is also a stop gradient here. And there is also because the language model learns from the lossy speech tokens, and it loads some paralinguistic information or some like the tone, yeah. So I think this is also limits the performance of the language model. So my answer to what should the next speech prediction be like is like this, and the language model should predict the lossless speech tokens. And let's look at this curve, and I think as the compute scaling and the thinker-talker performance will flatten very quickly, and the lossless speech tokens and will just climb, the performance will climb with the compute scales. So this is also how we built our MIMO audio, and we let the language model predict the lossless speech tokens. So in main module we released two model. The first one is the main module base, and we think it's a GPT-3 moment for audio domain. And we scale the unsupervised next speech prediction pre-training to over 100 million hours, and we observe the emergent in-context learning abilities, which means that it can when we give 5 or 6 demonstration, it can do few short generalization across different audio tags, like voice conversion, like speech-to-speech translation, and yeah. The second model we released is the main module instruct. It is an open source 7B sort audio LLM, and as shown in the picture, and it can achieve sort of performance on audio understanding benchmarks like MMAU, MMAU Pro, and spoken dialogue benchmarks like B-Bench audio and multi-channel audio, and instruct TTS evaluation and instruct TTS Evo. So let's dive into the detail. First is the main audio tonizer, and we think the first rule for audio tonizer is the reconstruction fidelity. So it can preserve all the information in the speech. Our main audio tonizer has 1.2 billion parameters, and it is 25 Hz with RVQ8. So it means that it has 20 tokens per second, and we train our tonizer on over 10 million hours of speech, and the training loss is a combination of the reconstruction loss and the ASR loss. So this is a performance of our main audio tonizer, and we can see that it has a best reconstruction performance and on both Chinese and English. Yeah. The next is the main audio architecture, and as we talked before, the main audio tokenizer produces 20 tokens per second, and it's much larger than the text token, which is usually 3 or 4 tokens per second. So we need to reduce the length gap, and we also need to improve the efficiency of both the training and the inference. So we need to reduce the length of the speech representation. Here we use a technique of patch encoder and patch decoder, which means that we group 4 speech tokens from we group 4 timestamp speech tokens and into one representation, which means that it has the model received a speech representation at 6.25 Hertz. Yeah. And for generation, and the patch decoder use delay pattern design, and it decodes the representation into the 25 Hertz speech tokens. Yeah. And for the data, and we use over 100 million hours, and we have data pre-processing, data labeling, and data curation. And for the training, our training is divided into two parts. The first is the understanding training, and the second is the understanding generation joint co-training. Yeah. So for the evaluation, and we evaluate our main module based on speech continuation and few short in-context learning. The first is the emergent ability, and we show that as showing this plot, when the training tokens is more than 1 trillion tokens, and the model suddenly learns how to perform few short in-context learning. And the second part is about the speech intelligence and the general audio understanding. By evaluation under the in-context learning setting, we can see that our main audio achieves the best performance across speech-to-speech MMRU and speech-to-text MMRU and text-to-speech MMRU. And one point is that it has a smallest modality gap, which we can see that the speech-to-speech MMU is 69, and the text-to-text MMU is 72, and it means a smaller modality gap, and which is much better than other open source audio LLM. Yeah, and it also shows a great audio understanding performance, like in the MMRU benchmark under a file short in-context learning evaluation setting, and it achieved the best performance. And this is a demo of the in-context learning task generation, and I will show just one. Yeah. No. So.
Don't I think you need second screen if you want to share through Zoom. So maybe just skip the demo.
Oh, okay. Yeah, okay. Yeah, and this is a demo of speech continuation. Yeah, and I will skip this. And for the post-training part, and our data has audio understanding data and speech generation data and the spoken dialogue data, and we add the thinking for the both audio understanding and the speech generation. And this is the performance of our audio understanding and the reasoning part. And as we can see, the MIM audio instruct achieve the best performance across the MMAU, MMAU Pro, and MMAR, and MMSU, and many audio understanding and reasoning benchmarks. And for the spoken dialogue task, and it achieves the best comparing with other open source audio LLM, it achieves the best performance on big bench audio in both speech-to-text and speech-to-speech and multi-channel audio, and achieve comparable performance to GPT-4 and Gemini. Yeah. The last part is about the instruction. In Instruct TTS, it achieves a comparable performance to GPT-4 mini TTS in English setting, and much better performance than GPT-4 mini TTS in a Chinese setting. Yeah, and this is an example of the Instruct TTS performance. As we can see, this is the input text, and this is the instruction. And when we give this to our MIM module, and it will first think like it need to stress the 18 years, and yeah, and this is the generated speech.
I want you all back here. 18 years for my graduation picture. I want you all back here at 5 o'clock sharp in your caps and down, ready to say cheese. Is that clear?
Yeah. Okay. That's all about my talk, and we are hearing. And if you are interested in audio post-training and product research, and want to cutting-edge audio research and build sort of open source audio, and come and join us. And this is the demo page QR code of our MIM module. You can check more demos, and this is my WeChat and my email, and you can, if you are interested, and you can contact with me. Yeah, that's all about my talk.
Yeah, let's thanks Don again. For the slide, we'll share through the Google slide. So for people maybe see farther, you cannot see properly on the red, feel free. And Don will be here after the talk. But I'm happy if we have one question for Don. If any, feel free to come to here on the MIMO model. Go ahead.
Thank you for your great talk. And I want to ask, can you elaborate on the, your data set is very large, over 100 million hours. So can you elaborate on how do you guys, collect the data and cleaning the data and the data collection pipeline?
Yeah. For the data cleaning, and we use a similar pipeline to the the EMNLP pipeline, and it has like audio normalization, speaker evaluation, and VD-ASR, and no, we didn't we didn't filter in many data, because our principle is that for the high quality data, it can be used for generation, and for the low quality data, it can be used for understanding. So we didn't filter many data, and we try to use all of the data. Yeah, and you can check our paper for more details about the data part. Yeah.
All right, so Don is here. If you have question with Don, feel free to chat. Yeah. outside, yeah, and he's recruiting, and yeah, with a big team. I know he burned a lot of GPU. All right, so let's have the final talk, which will be myself, and I will make sure everything on time. So I'm happy to sharing about the final perspective of multimodal agent reasoning and look something in the next. And for the talk today, from Larry, we see how agent in the past and in the future can collaborate from the conversation perspective. From Andrea's talk, we learn more about speech language model alignment. And what else? So this is Huck. A lot of you maybe know me. So I'm not sure how many of you attend the interspeech tutorial. Not much, so no worries. Each time I make a new slide, this is my bad habit, but so totally unique. So for my part, I'm gonna talk about multimodal speech agent reasoning. And for my part, there's a two section. The first one, I'm defining speech agents. So for Andrea's talk, we can see how ASR language model do pipelining and eventually get better result. And then we are connecting the idea about ASR, like ASR LM, to the definition of agent, and look at, as a system, can we have new evaluation for speech agent? In the second part, we are tackling quite hard topic about reasoning traits and how reasoning traits can help your model, not just speech model, also omni model, for a better agent with the speech understanding ability. All right, so before everything, let's look at this. So there's a leaderboard called OpenASR leaderboard. If you look at the y-axis, the lower word area is better system. The x-axis, the more data and model scale. And we can see there's a model called Canary recently got a better result with a lot of data, open source, and with a low word array. So the word array is actually improved roughly about 20% about the first version of Whisper. But one thing else, if we have more data and more modality, we can actually see Qwen 3 Omni also can have a better result, nearly as the Omni language model instead of a single encoder-decoder model like Canary. But if we think outside the box, there is also task and skill, which can also improve the general performance of your model. So saying we have the ASR language model, like the paper with Andreas on ASR correction, and meanwhile, we also have a paper 2 years ago in EMNLP called Whispering Llama. So directly plus you whisper with Llama, larger model, larger latency, but better result. And more recently, we have the MOE architecture doing the ASR, OCR, machine translation together as a pipelining system. So what is the definition of agents? Like people talk about agents all day long. So from the definition from the famous textbook, we can see an agent anything that can view as perceiving its development through sensors and acting upon the development through actuator. So it's kind of sparse and highly related to reason model. Think about this way, model versus agent. So for model, if I see an emoji of sushi, and we got something like, oh, this is a sushi, something like understanding. But what's the definition of agent? So there's two main components. The first one is autonomous. The second one is go direct. So if we think about this way, saying you have a model with consider sensors, the model 1 and model 2 like cooperate with some kind of from sensing to the planning. And then the model 3 have the actuator, which will interact with the world. So the sense, that's model 1 sense the world, give prediction to model 2, and model 2 get all the information to plan. And finally, we have a like text to action model Larry mentioned before, and we have an agent system. But if you really look into the connection between model 1 and model 2 is actually ASR language model pipelining, but now we have a better name. So think about this way, why we not just need a single language model, but we also need augmented language model. So saying about calculating a math question as an example, something we can see here is not easy to understand. Even as a human, we need a calculator. But if we directly use next token prediction to get the actual token of these questions, is likely is not a perfect calculator as a language model. But if we have an augmented language model, we have tools, we have memory, we know where to sourcing back to the value about a certain kind of rule or principle-based calculation, you have a better and more robust system. So the overall idea about agentic system is we shaking hand between each model and to have a best performance. If we will think about this way, speech models versus speech agents. And the things about the diagram will be from signal autonomous to voice go direct. Saying you talk to a system and eventually want the system to perform. So what kind of speech agent they have? So early work, one is audio GPT, the other is speech GPT, where Don was first author. Now think about this way. So directly talk to a ChatGPT and ask ChatGPT to assign some audio APIs. So this work, I think, is have been done in III 24. The main idea is just collecting the script to that language model to call API, is somehow get a GPT, like a general model with a general audio understanding. Meanwhile, another perspective is consider everything as a discrete token, and then you output as token, but you can convert this token to a unit vocoder, and finally to understand this thing better. But if we look at this definition with more than one model, what kind of evaluation we have? One thing more recently with Professor Chu from Kyoto University, also in the room here. So we are thinking, can we zoom out a little bit and have evaluating a whole system as a like pipelining? So we have a word called speech IQ. So you have a voice input, and then with motivative idea about how human calculate their IQ, they have 6 there, it'll bring the last 3. We have apply, understanding, and remember. So think about whatever system you give it to the measurement, and you want to get IQ to evaluating this system. No better is end-to-end, cascading, or something like a thinking model. So pipeline like that. So you have a voice, and then you give into a certain system, and then you get the word array. The word array is something like remember, you remember your the neighbor's name, something like that. And then you want to guarantee some understanding ability, like similarity between chat LLM. And finally, we want the answer ability, like applying the knowledge they have for next token prediction. So interestingly, we find out actually cascading system perform really well. And you can say, okay, this is some work we done last year. So could Omni like have a better version, Gemini have a better version. But the takeaway here is we can actually motivate humans' behavior, creating new like ensemble-based matrices, and trying to let that matrix eventually more simulating humans' behavior. And one thing for pipelining or agentic model is we are always grows together with the better individual models. And more recently, in EMNLP this year, also from Professor Chu's group, so they introduced cohort generated error correction. So the idea is in the past, if we consider a pipelining system, we have the embed, we have the rewriting, but can we also, as a general system, do multilingual and translation? And can we providing the decoding text as a pre-training resource for both sampling based, Bing search, and eventually have better result? The short answer is we can do it, and the result is quite exciting as a resource. Now, if we zoom out a little bit, saying about how we look at this Model 1 and Model 2 connection, you can see either Model 1 and Model 2 connect to each other, they have a better solution, but it's not as a definition of traditional matrix. But what else? If we zoom out a little bit, as an omni agent, what kind of C we can have? One example is here, like the Omni Vici just released 2 weeks ago, open source. The idea is, can we design like an Omni model with really little resource? When we train this model, I think we only use 4 to 10 nodes. It's still relative. If you do LoRa fine tuning, you can use one A100 node, still can make it. And we're showing off saying by having some kind of Omni model alignment, audio is important to let the vision language model to sense the real world. So there is some detail about temporal grouping. I will not go through it. But if you think about this way, is how audio helps VLM post-training. You can see with or without audio, actually the model understands the real world better for the video understanding. And in general, compared to QN2 Omni, our average reward is actually most smooth, and we are way better. Sorry, Dong, I think we actually have a good result on MNAU, and it's slightly better, but we are bigger model than Xiaomi's one. But it is actually good to see a lot of open source model happening. And one more thing is, can the model eventually do audio in and action out? We have this kind of setting to have this might be model doing some quantization and put this model on the robot. And finally, this thing worked pretty well. I think we have a video here. Let me see how much time I have. Right, due to the time limit, I will not go through it. Yeah, it's okay, we just skip it. So you can scan the QR code and you can enjoy the video. So it's about 2-minute video talking about what kind of tasks we included.
Hello, we're excited.
So right, is back to the schedule. So we still have 20 minutes, but let's look at something in the next. Multimodal reasoning with agents. So I'm gonna talk about 2 ideas. One is the reasoning trace. The other is multimodal reasoning for speech agents. If we look at the reasoning language model, the idea is compressing syntax thought process due to the training, and then we have the thinking token, and the thinking token will make the prediction. But this is a little bit different compared to the old definition of causal intervention. So we don't know the main mechanism is under intervention or not. But we base on the result to structure our probability graphical model. So let's think about the definition here. Why the fine-tuning have limit ability, as we taught in the previous section, is we want to let the model learn a policy to identify the actual response instead of hard memorize a single token. And as this year, people find out if we only do in-distribution fine-tuning, both SFT and IR can make it when the model scaling over training compute. But if we want to have some out-of-distribution generalization, you need both supervised fine-tuning and reinforced learning. That means you can do reinforced learning, which convert faster, and then you load your model for reinforced learning to make it more generalized. So, but if we know both we need hard memorize and policy, what kind of thing could be as the audio agent? Let me give an example. Can you play this audio? So, yeah, so it's possible, but a single audio signal, there's different textualized representation. I think different audience sitting in this room will have different, ontology about what something about inside this audio. They can be a non-human creatures, they can be emotion flow of a female voice actors, or you immediately come through with a Pikachu. But if we want to really train your model, what kind of like methodology we have behind this behavior? So saying we have a signal, as you see, there's many texts. We kind of compressing the signal to your own reflection. You have more text, more generalized doing the policy learning. But eventually you want to recover the signals through the text-to-signal learning and to make your model much generalized on the word model understanding. Okay, that is my hypothesis, saying one signal can reflection in reflecting many text representation, and eventually we do this kind of training, we may have a better model. Remember this hypothesis, and we're gonna use it again in the following reasoning work. Oh no. All right, so yeah, let's look at this ontology. So if we want to make our model multimodal reasoning, what we have a vision and audio content. What we want reasoning trace. Thinking about the Pikachu voice, there's a lot of weird thing about why this guy playing a Pikachu voice in EMNLP tutorial, but it makes sense. So, but what you really want this connection is, we want to make the reasoning trace, how we can make it. So we look at, when people really make the reasoning, we compress train of thought, right? So maybe from the reasoning trace, before model rewriting, we need COT. And before COT, we need multi-choice questions. And more before that, we need dense caption that recover the multi-choice questions. So if we want to do the multimodal reasoning through certain kind of voice agent, we need to recovering your train of thought, we need MCQ, we need dense captioning. Then we can have the reasoning process from multimodal to the text. So I'm gonna introduce two work with the NLP team with NVIDIA. The first one is something quite interesting. They call long perception thoughts. So distilling system to reasoning for system one perception. And the second one is more reason. As a speech guy, I also work on computer vision for half a year. And they call it long grounding thought. So doing the compositional vision reasoning chance at scale. So remember the hypothesis, like we need a reasoning trace and we want to generate it for no matter what kind of data we have. So try to answer this question. I know it's a little bit small on the image. So the question for a standard VLA reasoning question is like, what is written on the top about the green pen pillow? It's really small, but we want the model to read it. It's impossible. But the standard model, like human, they directly going, oh, I saw snow, and then they directly select the snow. But if you look at looking carefully, like the one we share in the Google Drive, the QR code, you can say, let me look deeper, and then eventually they verify, setting in the sub goal, and eventually do the backtracking. All right, so we want the model know when to think, when to stop, and then eventually to answer this hard question, because we want our model be generalized as being replacing as a system. So what can we do if we want to generate this long vision language reasoning trace? Saying you have a captions, one good caption resource is Dolce data from Google, which providing high quality human captions. So if we want to generate training data, saying you have a caption image like this, and then you generate multi-choice questions with your text model based on your meta captions you have, but you want to make sure the MCQ makes sense. So the second stage, you use VLA-and to generate sample COT. So the VLA-and kind of really look at the image to generate COT, then you use your reasoning LLM to extend your reasoning ability. How does these things help? If you look at the benchmarking result on the Cohen VL, like people pushing on the reasoning every day, if we're adding internal COT, we'll have 1% improvement. But just with 30,000 image with this like reasoning trace extension, they can improve hard reasoning question by 3%, which is non-trivial. Okay, so let's say, okay, Hak, you are a video guy, you are an audio guy, so what kind of things connect to omni-perception? So the questions there is, if we really want to generate physical aware MCQ, using the caption only is not ideal because caption itself sometimes limit. So at that time, we proposed idea to generate your MCQ with your bounding box. So think about this way. If you're a vision guy, bounding box is the textualized vision information. They writing the vision information in the bounding box with the XY information. So if they can properly grounded this vision information well in your metadata, you will make the multi-choice question much harder and eventually understand the image better. So eventually we find out these things improve the result extremely well. And one more crazy thing is training with these visual reasoning traits, on testing, they actually understand general things well. So they have improvement on EMNLU and then AU, which is really computing result, by only text image reasoning trace. Here I give an example. So there's a example from SpongeBob. So they want to understand what thing happened. There's a two video playing, audio playing inside, but they want to know why they make this response. But now, by training with this reasoning trace, they can know when to think and like localize audio patterns. All right, so kind of we know there's some continued overlap on the like signal to text and recurrent the word model, and even visual reasoning trace have omni perceptions. So let me give a further example on the audio understanding. One example is, can we make audio language model learning on thing new tasks, for example, voice quality affirmation. So the input is speech or audio, the output, how good is this audio quality is. So being the same hypothesis on the conceptualized, like textualized audio, without giving the real audio to the language model, you can give meta information, saying speaker, gender, signal to noise ratio. So this meta information kind of reflecting this audio in form of text. And then you do the filtering, you kind of make your model learn the audio even without listening through. Then you can redo the process again to making your Morse score like with the, a better ASNR, worse ASNR to make A/B testing. And A/B testing is actually the format of DPO. You can make the response selection. And eventually the model will learn the pairwise information from your text model, learn from textualized audio, and your audio model learned from the real audio and made a real prediction. Interestingly, this thing worked pretty well. We hired a human crew to calculate the coefficients. The person's correlation is over 8%, and if you do more DPO, actually the correlation and the result is better. All right, so now we know how we generate the reasoning trace through captions. We know the hypothesis about like textualized audio, but how they relate to the agent. So if we think about the definition of ASR language modeling, cascading agent are task and scaling. It's kind of my statement. And if we do the cascading, for example, you do a streaming ASR model, and then you do a refixing through another Omni model. In the netcode this year, we achieved state-of-the-art and open ASR leaderboard, CoVoS, OCR. But it's a little bit boring, right? So we have been working on this direction for 3 years. So can we bring something new? Yeah, we do. So so for the new work, also in the Omni Vici, so we have a work in my voice. It's called speech hands. So better ASR language models through parallel cascading. Saying you have both the audio, you give it to a streaming ASR model and Omni model, but this time you can let the Omni model to know, okay, this time I should use the ASR external model or themselves to make the final prediction. So in the paper, in the appendix, you can look at, it's now like interacting each other as two models, and then they can choose which transcription they want. From the result, because we have to build some core source model and our friends model to show these things work, and we find out if we treating the ASR model as a data store retrieving through this kind of rack actions, you can actually achieve new state-of-the-art in the OpenASR leaderboard. And the improvements are perfectly well. So there's a new question. What is the actual Oracle performance in the agentic era? So in the old way, if we have a single ASR model or a translation model, we saw the Oracle is all about your decoding. But now you have 5-4 model, and each model, like Andrea's recent paper, each model can have different Oracle, right? So what could be the actual Oracle like achieve new state-of-the-art? Is a way David beat Goria, right? If we can properly formulate that. So if you look at that, like this figure I'm showing here, the y-axis is what error rate, the lower the better. You see Whisper have a 7.1 and Quen Omni have 7.2. But if you directly use text only, you use Quen Omni to do the corrections, not always guarantee a better performance. But if you look at each Quen Omni and Whisper's best result per sample, the actual result is better. That means there's more thing we can achieve as a agentic system by properly make a proper selection of the output of each model. Okay, that's my hypothesis. Let's think about this way. Different models are good at different perceptions. We have ASR model, audio model. So ASR model is like a knife, like good at transcribe and knows robust speech. Precision for speech instruction. We need the ASR, we need the translation. LLM is like semantic and non-semantic understanding. We have rich sense captions. But if we also think about OmniLM, it's more like joint modality understanding, but often not to be the best model. So if we want to work together, why not just treating language model as a task and operation system? And then you have this operating system, an Omni model. You're saying you have an audio. You can saying, okay, now we use ASR model because I'm this confident about this audio. Or this time use audio model. Sometimes want to use audio from Mingo, like other audio-based encoder-decoder model. Or sometimes think myself. Okay, I got audio result and want to think and then got a better result. So maybe I would not that's the best way, but maybe there's more abstraction things we can do as the joint system for audio agent. So here's the pipelining. It's also work with my former intern here. Is we have a reference agent, we have Omni agent, and we have external response, internal response. And then since we can do alpha decoding to know in which time which response is better, and then you add your Omni model to make it better actions. And finally, you get output. So think about this way, it's like you do the training about your training data, you want to make a better selection and then to get a better S1 score and eventually do the evaluation, right? So it kind of makes sense, right? So how good it is? I think in those results, we see the 74 was the state of the art. And in this work, we are pushing the archive. We even further pushing the result, we got 77. You're saying, okay, how it's possible overfitting, but it's the way you can agenticize your model and to make your model overfitting are the task you care eventually, right? So if you also think about ASR performance, for the OpenAI leaderboard for earning, they don't have a training result. So all the result here is like we train the action selection in the training set and report the result on the testing set. As you know, we don't use further data. It's possible to even better, more generalized. But if you look at those results, it's actually a really big improvement. So that means it's possible not just directly do the serialized cascading. You also can have more design space there. So as an ASR language model person in 2020, you see ASR model is bigger and bigger. So we have the generated error correction. So now we see, happy to see this here in EMNLP, we have more correction paper. But if we think of this way as a summarize of this section, maybe we have more speech language model. The first one is agentic. They have a better performance, but higher latency. Something don't cover, and I will solely cover later in one slide, is there's a duplex language model, low latency, and be pretty fast. And finally, there's Omni model. They do the multitask modeling. They have semantic here, but they have a text decoration ability here, but you can do text balancing as an audio injector language model. But for the duplex, indeed, the key difference here is like there is a syncer channel, tool channel. You need a multi-head transformer prediction. There's more thing to think, but it's possible to have more design this multi-channel way. So okay, so let's have a summary. So in this section, I keep it good style and hope I balance those things well. But we have a speech agent background and multimodal reasoning. And now it's a summary. If we really look at something about speech agent with language model, we can think of something next is a general signal understanding. Not just treating the audio as noise, not just treating speech as a noise. You need to consider multi-resolution of your sound landscape. And then as a thing I always working on is the speech language super alignment. We have to kind of handling the weak to strong alignment there. So here's the final remark. Do we need a better ear or better brain to recognize voice or understand text? Again, I think we need both. And there's more design space about like doing that within the model or as assistants. So what kind of agentic-based evaluation for speech we need? So one thing is that from word array should be eventually ensemble your matrix as task completion rate. So again, perfectly on time. Thank you. And we have open QA. Yeah, appreciate it. Yeah, I think we can have questions. Yeah, go ahead. Please go to the microphone.
Thank you for a wonderful talk. So I have a question about the parallel cascading. So what's in the intuition behind the feeding the ASR text into the LM besides the audio input?
Right. So we know the ASR text, sometimes there's more information, right? Because for the audio LM, they care too much on semantic. So they can over focus on your phonic when you're referring to ASR history. Then the ASR arrow can helping the understanding eventually if some kind of special term company then didn't recognize well. Okay. Yeah. So back to our hypothesis saying memory is something important if we have a cascading system.
Yeah. Okay. Thank you.
Yeah. Any other questions?
So you had some slides about visual grounded reasoning, and maybe those can be expanded to maybe audio grounded reasoning as well. But my question is, since we're mostly using LLMs as their backbones, the reasoning trace is in text, and sometimes text may not be sufficient to describe like what part of the image you're referring to or like what exact element you're referring to. So does that
yeah, got your point. So it's really hard to align your non-text information in from a kind of text, right? So for that, actually, I think as a multimodal person, we should really look at is that internal language for language model to represent non-text. For example, now when we do the post-training alignment from vision or text, is we're forcing the textual tokenizer to learn some weird token about audio and video, right? Then there's two ways. One is we want to really find out are they high frequent like textualized audio representation in discrete fraction, or we just realized are there something like intermediate guiding text to let the grounding process become better. But seeing both directions is still unknown.
Okay, thank you.
Right. Yeah. Yeah. So we can have a final questions, and I will still be in the room. And yeah, any other questions? Yeah, go ahead.
Thank you for your great talk. And I want to ask, how do you think about the next generation audio LLMs? So, in my opinion, so the next generation audio LLMs, it must be capable of reason complex tasks. For example, I hold a bottle of water, and I drop it down to the ground, and I hear the sound back to my ear, and I want to the AM to calculate the gravity, the G, So to achieve this kind of task, this kind of complex task, what do you, how do you, so what should we do to accomplish? Speech, your slides show some, thinking, the reasoning task, something about reasoning. So how do we formalize the think steps for the audio modality? Text modality, we can use text as the intermediate steps to
Right.
Yeah. So how do we think? How do we formalize the audio reasoning steps?
All right, so I think let me reformalize your question. Actually, you have two questions. The first question will be, what is next generation of audio language model? For that question, I have a hypothesis. It depends on how much you want the language model be smart enough. So for example, calculate G from an echo is beyond humans like common sense, right? So I think there's two ways. One way is that you make the model extremely smart to unifying time series, audio, music, and speech signal together as something kind of like signal super intelligent. But meanwhile, we see human behavior like conversation, kind of meta information. There's also have a conversation robust like understanding. But from my perspective, I think both direction will be there. So, but I feel there's unknown direction how we unify all the signal in the multi-resolution from the alignment space. But meanwhile, if we do the duplex model, like doing the signal and text interleaving, the issue is speech is least sufficient than text. So then that all the pre-training problem become post-training problem. Right. So, but if we look at a signal super intelligent from scratch, that may be a way we do least data but have a better understanding of the signals. So if we come back to the reasoning, why we really need reasoning, people, the dark fact is like not always all the tasks need reasoning for audio, but reasoning helping audio understanding. So I think both direction will be there. Like people often ask me these days, like speech AI stuff is quite popular these days. They're saying, okay, duplex model is better or cascading ASR language model. I think there's different kind of human beings, right? So there's people like speak fast, there's people think slow. So I think both system will be there, but I think we kind of need more diverse system, and per system we need to narrow down what kind of actual, product or scenario we want to use. But I don't think maybe they'll have a unified system. Or if we have too many data, it's possible. But due to the nature about speech language alignment, I don't think that will be true. So both answer will be more diverse. Yeah. All right. Thanks again. No delay. Thanks a lot. All right. For the slide we are sharing in the underline. So if you need it now, you can just also let me know. Yeah, there's a good QR code at the first page. Can you come to the first page? Yeah. No, first page. Yeah. Now is 25th. Yeah. Yeah, this one. Yeah, you had. All right. We are not there. Yeah. Cool. Yeah, thanks again. Like even we have overheat issue on the projector, we still almost full for the second. Appreciate it.